Hey Sean, how's it going?
Good, Hans. How are you?
Good, good, good. All right, so is my audio video coming in loud and clear for everybody?
Yeah.
Great. All right, so let's start off here with a quick intro. So I've told you guys a little bit about my work with Sean, but probably haven't done it justice, and also in terms of describing everything else that Sean does for the university. Um, so yeah, maybe I'll pass it over to you, Sean, if you don't mind, just kind of giving the students here a quick high-level overview of, what you do. The students have been exposed a little bit to Tableau. So you could, talk a little bit about, you know, that tool from your perspective. And then, yeah, maybe finish off with your perspective on the sports data work that we've been doing with the Department of Athletics.
Sure. Thanks everybody for having me. My name is Sean Hoffman. I'm the Assistant Director for Analytics in the Division of Educational and Institutional Effectiveness. We're out of the Office of the President. So I'm mainly responsible for the development and delivery of Tableau dashboards through our university's Tableau server. We have somewhere in the range of 300 to 500 users who we build self-service tools for, ranging from academic units, so dean's offices, to chairs of departments, to the provost office, the president's office, all the way to student services, the registrar, bursar, financial aid, everyone across campus who needs access to data. We build those tools so they can go in there and pull their own information. So that involves building the data sources, maintaining the data sources, building the actual dashboards themselves, managing users, training them, and kind of going through the education process. Part of our mission is educating folks on how to use tools and how to leverage data to do their jobs better. Um, I do have a little bit of responsibility for data analysis, but it's mostly now living with the self-service tool delivery. Through that, we've branched out to other areas on campus. Mostly, I work with student data. We started with that. We work with financial data too, human resources data, research data, and now athletics data. So we've kind of rolled into everywhere where people want to look at different data. We'll pull it into our servers and we'll push it out on a dashboard. Hans had worked with me before on delivering a different project through the School of Health Professions, and then when this came up, said, "Hey, do you have any capacity to do this?" And I said, "Yes, please," because I do enjoy
Mhm.
working with data, but I also really like Stony Brook and I like Stony Brook athletics, so this was kind of a cool project. We are basically pulling in data from the athletics database into a Tableau dashboard that's being delivered to the athletic training staff right now to monitor metrics for different things they want to look at, different speeds, different practice metrics, different exertion um, data. And so we're in the testing phase of football. I think next step, Hans, FYI, is I'm gonna ask about soccer, and then we're gonna go from there. But that's kind
Nice.
of the at large, what I'm responsible for on campus. Hans, do you want me to go anywhere else, or are we good with that?
Yeah, no, I think that's awesome. Yeah, so Sean wears a variety of different hats, touches a good chunk of volume that's generated within the university, like you said, mostly from, an academic and administrative perspective. But when we have the opportunity to collaborate, we try and find ways to collaborate. And I think Sean could also kind of talk. Well, actually, maybe quick question for you, Sean, that would be helpful
Mhm.
for the students. How did you get into this role? Like, how did you find yourself becoming this
Sure.
sort of dashboard master for Stony Brook?
Yeah, so I'm a Stony Brook undergrad and grad alum. So I did my bachelor's and my master's at Stony Brook in the Applied Math and Statistics department. Um, and going into my senior year, I kind of had a couple conversations with folks on campus I knew and said, "Hey, I like data. I like Stony Brook. I don't really want to leave. You guys want to pay me to do stuff?" And they were so gracious as to give me an opportunity to be a graduate assistant. And then that turned into a full-time job and kind of rolled in from entry-level data analysis, really started with cleaning Excel files. Like it was kind of basic. And then when we built out the desire, we built out kind of the capacity to deliver some tools, some Excel dashboards and some things in like Power Pivot, and Tableau Reader was kind of the first frontier. and then said, here's what we can do if we have some investment, got senior leadership on board. They invested in Tableau Server and we went off and running. But that was a process. I started in 2014. We got Tableau in 2016. We got the server in 2018.
Nice. Yeah,
Yeah.
so Sean's absolutely critical for nearly any type of data request across all of the different schools that Stony Brook has. I'm sure you know how many schools we have off the top of your head because I don't.
Oh, 11.
11. Yeah.
Yeah.
Yeah, exactly. So before we jump into presentations, does anybody have any questions for Sean as it relates to his role or, maybe his career trajectory, or anything that you sort of might be interested in?
And before they pop up, I will say you don't have to just have them now. If you have them later, Hans has my email, so feel free to shoot one off. That's fine.
Yeah, hi, nice to meet you, Sean. Thank you for your time.
Sure.
So I know you've constantly said like you're responsible for basically all the data across the 11 schools,
Yeah.
but we've only been interacting with you indirectly through the athletics department.
Yep.
What is another like major avenue of data apart from the athletics department that you kind of interact with?
It's the biggest source is PeopleSoft. So everything that you all do from a student side, so registering for courses, enrolling in a term, all of your billing that goes through there. But it's mostly the academic side data. So your courses and your term enrollment is one of the largest things we look at. We look at how many courses students are enrolled for, how many credit hours are being delivered across campus, which majors have enrollment, minors, up, down trends, application data. So anything when you guys go into solar, that's PeopleSoft. So that's one of our biggest repositories of data. Employees have all their information in there too. But the kind of our bread and butter in the division, the first thing we really got sorted out was enrollment. How many students are enrolled every semester, and what does it look like over time?
And how long has your total tenure been with Stony Brook thus far, including undergrad then?
2008, I entered as a freshman. So we're getting up there. We're going towards almost 20 years. But yeah, it's been a good run.
Nice, thank you.
Yeah, sure.
I had a question regarding this is Yasa. Um, I work in Catholic Health, so always interested in data transformations and stuff like that. You mentioned PeopleSoft. Do you have like replica of that data sets, and then Tableau accesses that, or what are your best practices, I guess, when it comes to
Yeah.
that aspect?
So PeopleSoft Oracle is a transactional data system which it's always updating and so it's always live, and that creates the problem of figuring out what things look like over time. So as part of the division, we have an institutional research office that does data analysis and official statistics. We have an assessment group and we have a data warehousing team. I work with all of them, but the data warehousing team hosts a Stony Brook Data Warehouse is a Microsoft SQL Server environment that pulls in all of the data nightly. They're moving into Fabric, Microsoft Fabric right now. It's going from a warehouse to a lake house. We're doing that kind of transition. But right now it's a Microsoft SQL Server environment. It takes frozen snapshot pictures so we can look at what it was like on the official enrollment day of the term, which is the 15th day of classes. We can look at what it looked like yesterday or the day before for some areas, but we're kind of bringing it over, freezing it over there, and having those frozen looks at things, and also the ability to hit the transactional side. So once it's in the warehouse, it goes to Tableau every morning, and it's just kind of a like a view into it. But all the ETL is done from the warehouse team. I do a little bit of building data sources, but they do all the ETL.
Yeah, I was just curious because we talked about MongoDB and stuff like that, so uh, just wanted to know what other shops are doing.
Yeah,
Yeah.
yeah.
All right, what else for Sean?
I have a question.
Sure.
What sort of decisions are you helping the different schools make with all the data that you're collecting?
So there's a lot of different ones around trajectory, right? So where do we think we want to go? Are we getting there? Are we have the right mix of students? Do we have the right mix of course offerings to meet those student demands? Course scheduling is one of those two that uses a lot of those data. We've informed some decisions too on, I think one of the ones I really like to use is there was we do an analysis on how long it's taken students to graduate, and we were looking and seeing that it was kind of ticking up on one department. And we talked to them and said, "Hey, do you notice anything?" They said, "Yeah, let's take a look." They revised their curriculum, and it was down within a year, right back in line. And so being able to see visually those trends have been helpful for people because some people, when they just get a bunch of numbers, go, "Oh, okay." But if they start to see the shape, it helps them go, "Ooh, that's good," or "That's bad." And so it's really, I like the word you use, inform, because people will say data driven, and I don't like that because I don't want to drive the decision. I want to help people who know what's going on really make that decision. So putting that tool in the hands of folks and then informing them is the correct way of looking at it. But those are some of those areas that we're looking at.
Yeah, one of the other big ones
Yeah.
that you helped with Sean, right, was the middle states. So there was,
Yeah.
so as you guys know, like Stony Brook needs to get accredited to actually deliver education and to be applicable to receive like federal funding and state funding. So Sean was also part of the team that was pulling together then all of the data to provide to the accrediting agency called Middle States, or I think it's called Middle States, right?
Yeah, the Middle States Commission on Higher Education.
Yeah. Another super important sort of task that he is and has been part of, because if we don't get accredited, that's a big issue.
Yeah, minor details.
Yeah. Briggs, I saw that you were about to unmute yourself.
Yeah, so I have this question. Hey, Sean, this is Briggs. So my question is, I don't know if within the scope of your work or not, but Solar and Brightspace, the UI and the UX is something that needs needs
Yeah,
some love,
I
needs
hear
some love
you.
and
Yeah, me too. It's like that for employees when I'm putting in my timesheet. No, it's so we have a separate applications team that manages PeopleSoft, so we're just kind of hitting the data and using it. Um, and Brightspace too is delivered by the applications team. But I
send
but
in
I
some
but I do
send
hear your point.
send in some love and pressure to these guys. I mean, come on.
Yeah, every now and then when I get them in a room, I just pull it up on my phone and go, I can't log into my timesheet here. So yeah, I hear you.
Sean, thank you for being here.
Yeah.
Um, how much have you seen, or have you seen AI as a big help, or do you see it as a challenge in what you do?
So on my side, because we're doing a lot of custom things that are really like university specific, it hasn't really helped or hurt me yet. I'm noticing a lot of folks that it'll help them write code easier too. We've seen that, but especially in institutional research where I partner with that office a lot, they're doing some bigger analyses on surveys, which is helping with text analysis. It's helping with kind of thematic things, which is really good. It does help write initial drafts of large summaries too. Obviously we have to check all of them, but it's helpful with that kind of work because mine is more building a little visual tool. And I've noticed the Tableau AI is good, but if you don't have good metadata, it's not great. So, and we're kind of going off of an older system that wasn't set up to have metadata there. So that's kind of the next phase is how do we make that? There's a whole data governance council that's working on definitions and things like that. But I see its potential, and I see it's working over in the areas that are doing some more qualitative analyses. But in my direct work, I haven't worked too much with it. I watched way too many sci-fi movies when I was growing up, so I'm semi-scared of being in the Matrix, and I'm a little bit hesitant, but that's just me.
Thank you.
Sure.
Hi, Sean. My name's Nawal. Thank you for being here. My question is, what's like a big problem that you guys are seeing, at least with like your team and everything on a day-to-day basis, that you would also maybe like a skill or something that you would recommend for us since we are trying to enter like the job field or like
Sure.
break into this type of field?
I'm kind of spoiled because our team's really good, and I don't see many problems with us. Some of the problems we deal with is more external pressure. The federal government needs this today, or the state government needs that. On the skill side, though, I will say, a lot of folks will put fluent in Excel on their resume and don't know how to do VLOOKUPs or pivot tables. So fresh out up on those. They're really, really helpful. Excel is used in a lot of areas. And then SQL's great. I use it all the time. I taught myself to be a SQL programmer now. So those two skills I use all the time. Tableau's good. I think you guys started looking at that. And then a little programming here and there. Just kind of knowing the ability to learn those on the fly is great because if I see you have some experience with a programming language, I'm not going to say, "Oh, it's not this one." I'm going to know you know how to learn a language, and I can teach you on the job market there. But as long as you've you're going to get that on the job training. But as long as you've a little broadened the skills a little bit into some sort of programming, some sort of data analysis, and some sort of visualization tool, you'll be okay. Whether it's R, it's Python, it's like SQL, and then you could do Tableau, Power BI, all that stuff, and then throw some Excel or SPSS in there, and you'll have a good mix of skills.
Okay, thank you.
Sure. The
All
follow-up
right.
question is being no, we don't have any open positions right now, but they'll be up there if there's one.
Yeah, whenever you have that in the future, Sean, we'll be sure to pass it on.
Yeah.
Um, okay, great. Yeah, so I'll share Sean's email with you all
Yeah.
afterwards. So if you have additional questions that comes up, I'm sure he'd be more than happy to help field them, point you in the
Sure.
right direction, or share his thoughts. Okay, so and Sean, so what I had said to you in an email, right? So the students are going to give us brief presentations, 10 minutes. We got about 8 different groups that we'll go through. And their analyses aren't fully baked out or fully complete. So, part of what we'll be trying to do is also field some of their questions or give them sort of some like live feedback. And also, the other students will be able to participate that are not within that group and also ask questions or kind of give their suggestions. So, it's really supposed to be kind of a constructive sort of feedback session. And then they'll be turning in their final reports to me at the end of the semester, which I'll then share with you. And then we could review and see if there's anything that aligns with, what could be presented to the athletics department. Um, Perfect. So with that, again, I'm just going to kind of randomly select groups here to keep everybody on their toes and engaged. So I think maybe the first group that we'll start with is, and I'm just going to go off of the group numbers that we had in the Google Sheet, is group 3. And let me enable screen sharing and stuff like that. So group 3 is Yatsa and Nina's group and everybody else that is within that one.
Thank you for that. I wasn't sure.
Yeah.
Thank you.
Yeah. And let me just shoot over the Google Doc here again for all of you, because I'm sure you probably haven't looked at this thing in a little bit of time now. So just sent over the Google Doc there, and we can see your screen, Yatsa. So whenever you're ready.
Yeah. Blanca will start us off.
Cool.
All right, good evening, everyone. I'm Blanca, and this is my team's sports data analysis. Next slide, please. We'll start off with an introduction, then we'll dive into methods, key findings, practical applications, and finally, the limitations that we encountered and our recommendations for future work. Next slide. Our hypothesis was, would players with higher asymmetry differences between right and left sides for torque and max force affect acceleration load and distance total results? This directed our research question, which is, could these key indicators be used to determine a player's risk of injury? This matters because multiple studies suggest that higher asymmetry differences between left and right side measurements for torque and max force correlate with an increased risk of injury. Next slide. To test our hypothesis, we observed left and right max force and torque from valve, as well as accel-loaded human distance total from Connexin. Max force measures the absolute maximum linear force that a muscle or muscle group can produce. Torque measures the rotational force produced by a muscle group. Accel-loaded cum quantifies the total physical stress imposed by a player's repeated changes in velocity. And total distance measures the entire distance a player travels during a competition or training session. We decided on these metrics because they are widely used in assessing injury risk and player performance. By using these metrics, we were able to calculate asymmetry and then use the results in a linear regression analysis to look for correlations between those metrics. Before we could conduct our analysis, though, we had to derive average max force asymmetry and average torque asymmetry to be able to quantify its asymmetry itself. We use the formula pictured here, where L is the left side and R is the right side metric, to calculate and derive asymmetry in max force and torque. Finally, we use those average asymmetry values to create 2 categorical variables, those being max force asymmetry category and torque asymmetry category, An absolute asymmetrical percentage value greater than or equal to 10% was designated as high, and anything below that was considered low. And next is methods.
As for the methods used in the project, it included reviewing the raw data to determine which metric had the highest number of the recorded values, highlighting and omitting any missing data, and recoding duplicate team names. The process also involved identifying players who were assigned to multiple teams. After determining the most frequently recorded metric, relevant topics in PubMed were then explored to help support the analysis. And we also used descriptive statistics, including means, medians, and ranges, which were then calculated to summarize this key metric. Correlation and regression analysis were also conducted to examine the relationships between maximum force, torque, accumulated acceleration, or distance. And finally, the findings were then cross-referenced with the literature review to provide some context and strengthening the interpretation of the results. And I'll pass it on to Nina, who will discuss some of the key findings.
Thank you. Regarding our key findings, symmetrical metrics such as torque and max force were reported on the valve data, whereas acceleration and distance were reported using Kinexon. Primary issues seen across multiple teams is that there is a drastic difference in volume of testing between Kinexon and valve device data. As seen on the chart on the left, Kinexon has more predominant volume of data compared to valve. Next slide, please. Difference in testing can also be seen amongst different teams with not just volume of device usage, but also with testing behaviors of teams. As shown above, football has the highest use of Vault device across the top 5 primary teams and a higher ratio percentage of Vault data to Kinexon data. But as seen on monthly testing, football has most of its data for Vault during beginning of semesters. However, when compared to women's soccer conducts more scheduled Vault testing. However, key issue with this is that multiple instances of Vault data is recorded without record of Kinexon data. This would make it harder to determine correlation between Vault and Kinexa data metrics. For men's data, like basketball, testing is slightly more sporadic, but has a large amount of Kinexon data values collected compared to Vault data. Primary difference here is that a small amount of data is collected for Vault that occurs during the beginning of fall semester and the end of spring semester. Next slide, please. When it comes to evaluation of player performance, there is not enough valid records to make correlation with data for Kinexon. As seen with players 1128 and player 1755, total distance has consistent data, but for both players, they have infrequent torque data recordings. Even though it appears that both total distance for both players decrease as torque increases, this is relatively deceiving due to the lack of vol data and the incline variation. For example, when you see player 755's decline of total distance, this is very minimal when compared to the incline of torque difference over time. As opposed to player 1128, there is a more pronounced decline in distance, but a lower increased average of torque difference. Similar issue could be seen in testing frequency metrics across all teams over time, where there is a drastic fewer instances that both VALD and Kinexon usage are present. Next is Yatsa covering statistical analysis of key findings.
Thank you, Nina. For our statistical analysis, we began with our t-tests using our performance metrics and our as our independent values and our categorical metrics as our dependent value. We chose this initially because we wanted to determine whether the asymmetrical categorization affected the accelerator load and the total distance. However, many of these tests failed because each category needed at least 2 levels to perform a valid evaluation. So we then proceeded with our analysis by treating the total distance and the accumulated load as our dependent values and our asymmetrical categorization as our independent values. So we also calculated the mean asymmetry difference to examine whether or not that there's a significant difference between the two groups. As you can see here, there's little to minimal difference between the means for the two categorizations, and the t-tests are very poor. Where the p-values are ranging from 0.3264 to 0.9979, all greater than 0.05. And the confidence intervals are all inclusive of 0, indicating there's no statistical significant difference. Next, we conducted a linear regression test to assess whether any of the metrics shows any signs of correlation. While some of our p-tests improved closer towards 0.05, all our R-square values remain low, closer to 0 rather than 0.3. indicating no meaningful linear correlation that we can ever establish. Then we examined our literature review to see if there's any significant findings. Our lit review indicated that athletes between 10 to 15 asymmetrical difference have a higher risk of injury. However, our asymmetrical averages for our data set were less than 2%. This suggests the majority of our participants displayed a mild asymmetrical symptoms compared to the ones flagged in our literature review. So why the disparity? We had to scale down many of our records from 44,314 to 383 records due to the limited paired data available between the bilateral and the performance metrics. This reduced the data set to less than 1%. Perhaps there's other factors contributing to the weak findings. For example, our study doesn't account for athletes' natural abilities to adapt asymmetrical differences due to age or physical abilities. There could be other factors that we're not reviewing. One of our PubMed resources indicated higher accumulated load can also increase risk of injury. So this suggests that we need to have more analysis to determine correlation. So next, Katiana will review our practical applications for our project.
Thank you, Yatsa. So as we mentioned earlier, the literature suggested that torque and max force asymmetry was correlated to an increased risk of injury. So as a result of this, we developed a flagging system using those metrics with a 10% threshold, which the literature also suggested was a common threshold to use. We also flagged players that were inactive for more than 30 days to determine or just kind of dig deeper into why that inactivity was occurring. Next slide, please. So the intention behind this was to develop a system where the players had a personalized injury risk model to help them understand their unique load patterns, and coaches could also help with load management to protect players from fatigue and improve endurance. So we were able to flag a small number of players with this method, but because of all of the unknowns that were mentioned before, we can't say for certain if they're indeed at higher risk of injury. So for example, some players were just tested more. So even if they did have a higher asymmetry, the question is, were they tested enough? And as for the players with the lack of testing for 30 days, we need to kind of identify why that is happening. Is it because of fatigue? Is it because of illness? Or is it indeed injury? Next slide, please. So we think the flagging system would be more beneficial with better data collection. So we would recommend that to test all players at regular intervals with at least one set of bilateral and one non-bilateral metric simultaneously. Weekly testing would also be good because not only would you get more data for asymmetry, the literature also suggested on a side note that the acute-chronic workload ratio is a good risk of injury detection. So that would be more data for that as well. Okay, so pass it on to Luke for limitations and future work.
So for the limitations and future work, data challenges that were encountered was first, we're dealing with inconsistent data entries. So like teams appeared in multiple different formats, like women's basketball with an apostrophe versus women's basketball without it, or like lacrosse versus lax, making it difficult to aggregate information accurately. And we're also seeing invalid entries like unknown or player not found. And we lack standardized codes to explain why data is missing. Like, is an athlete absent due to injury, illness, or equipment failure? Right now, we can't tell. Next slide, please. So our testing protocols also need work. So the bilateral max force and torque assessments using our full devices vary significantly in timing and output across teams. Most of the programs haven't established like a regular testing schedules, creating gaps in the longitudinal tracking. And additionally, when Vlad and Kenexon data are collected on the same day, but during different sessions, it complicates our ability to paint a complete picture of the athlete readiness. Next slide, please. So where do we go from here? We need to expand our data set to validate whether these metrics can predict injury risk. And we need deeper investigation into specific measures like max force and acceleration load. And most importantly, we need to examine the relationships between injury events and metrics like total distance, acceleration load, and force asymmetries. And that would conclude our presentation. So I would like to ask a question. Injury prediction in sports is still an evolving field beyond the metrics we discussed today, like force, torque, and acceleration load. What other factors do you think should be incorporated into injury risk models to give a more complete picture of athletes' readiness to compete?
All right, great job. So before we get into potentially coming up with some thoughts on this question, um, thought you guys did an excellent job. Love the recommendations. They're very actionable. Um, Related to the 10%, so when you mentioned that that's what's found in maybe like PubMed or somewhere else, uh, was that for like any specific sport or male versus female, or maybe just like expand on that quickly?
It was just about as your asymmetry increases, roughly about 10 to 15%, that's where you see a increase of injury potentially, as opposed to anything that's less than 10%. It could be just natural abnormalities or, natural slight adjustments like one or 2%. So we try to do a threshold of 10%, you know, being on the lower bound because it says 10 to 15. Um, but all of the average means were all like you saw it's like 1.93%. And I think it really boils down to we just simply didn't have enough data to compare between the two devices. That was very difficult. Um, yeah, like I said, it was like 44,000 all and at the end we only had 383
Yeah,
records. So it was really hard. We're kind of pretty bummed. We tried really hard to get some good value, but I think there's still value in the research. I think if we can get more data, there might be something there. Um,
great. And then before I pass it over to Sean to give a couple thoughts, how did you define inactivity? I like the concept of how you were trying to kind of it almost seems like figure out a proxy measure for injury. So maybe just expand on this inactivity concept a little bit.
well, the players, there wasn't, so there's more records, right? Each record or each metric, right, is one row.
Hmm.
So some players had more, some players had less, and so on. We also, I think Tatiana, you saw some players had were like in two different teams, right?
Yep.
And so they had measurements in this other team, but not in this one. So you're like, well, should I take this measurement or not? Because it's really from another, because we filtered it by team. So that got filtered out. So it's just kind of inconsistencies all throughout.
Great.
Um, yeah.
Sean, pass it over to you.
Yeah, no, that was great. I think, as you mentioned, there's value in the approach, right? Like even though the information wasn't what you wanted, that approach was excellent. I think I'm going to speak to all these projects more from the perspective of working with data consumers and working with data experts. So like when I go out to any data project that it's not my information like this, I would, partner with the folks over there to understand and ask the exact questions that you talked about asking. How do you do this? Why do you do this? When do you do this? What does this mean? And talk about the issues. So I actually did this with the athletics department. So I worked with their training staff to understand how do you enter these data and what does it mean when someone's on two teams? And I found out that often it means they're borrowing someone's device. So I actually, and Hans, I can provide you with this. We can work to get this set up. I've cleaned a lot of this since then, so I've gotten rid of a lot of dupes. I've put people on one team. So you and I can maybe take a look at that to see if that'll help folks. I can provide out the my clean version of what you have if we want to
Yeah,
work on that. Happy to
that'd be
work with
cool.
you on that. But so like I said, mostly I'm going to talk about just data approach and that's right on how you would do it and how you would suggest to work with them. I think if I remember correctly, they are looking at imbalance in some of their reporting, and so I think they would be interested to see that, doing it more would be helpful for them. So that's great.
Yeah, I think very, very actionable. And from the perspective of this question, very thoughtful, interesting question, because I think we got to first start off with how do we define injury, right? There's probably different degrees of injury. There's like a season-ending injury. There's like a, just injury that ends your complete NCAA career and, something that could be like very traumatic, right? Or there could be something that maybe is like a sprain, strain, where it just like decreases your ability to perform at a high degree, but maybe you're still game ready. Or maybe it's an injury that actually takes you out for a couple weeks. So I think that's one of the big deficits that we don't necessarily have right now.
Right.
And maybe Sean, correct me if I'm wrong. I imagine that there's some other system. And I think Vinny was like telling me that they do track, or maybe our athletic training team does track injuries and stuff in
Yeah.
some other system. But
Yeah.
I didn't I don't have HIPAA on Tableau, so I wasn't gonna touch it. But yeah,
yeah.
that would be good.
Yeah,
No,
but in terms
yeah.
of we do have that data though, or no?
I don't have it. I
Yeah,
would ask Vinny might.
yeah.
There were some candidates that had like 80%, 60%, but we had no data. So like you could assume it was because of injury, but you're not sure
Mm-hmm.
because it was a short range. So that's what we meant. We weren't sure. We can't
Mm-hmm.
definitively say, oh, but they only have one entry. So my t-test failed because there's only one dot and that kind of
Yeah.
thing. Yeah.
Yeah, and anecdotally, I mean, I remember I was having a conversation with Vinny. I said, "Hey, looks like one of your wide receivers like missed this practice right before the game." He said, "Oh, he left his device on the bus," right? So like, there's all these things that just can happen in
Right,
there.
exactly. Yeah.
So as you said, it's maybe this broadening and continuing to test, and sometimes that's a fine result, right? Sometimes I'll work on a project with folks and say, "Hey, we need to collect more and come back next year," and but with the right approach, like you suggested, which was great.
Mm-hmm. Yeah. Great. Yeah, great job, guys. Opening it up to the rest of the class now, quick. Any questions or thoughts or feedback from the rest of the cohort here for this group? Going once, going twice. Wait a few seconds. Okay, great job. Okay, excellent. Nice way of kicking things off. So now let's go to lucky number 7. This is Cynthia's and Kaylin's team.
Yep. But the camera's gonna screen sharing.
Okay.
Just give me 1 second. Oh wait, wrong one.
Mhm. All right, we can see your screen now. Feel free to begin whenever.
Okay, so to get in, so this is our presentation, athletics performance analytics, and my name is Tanvir, so I will be starting it off. So our project focuses on understanding how the five key metrics vary across athletes from multiple different collegiate sports. Our research question asks, how do system weight, peak velocity, jump height, peak propulsive force, and average propulsive force differ between sports, and how do these values compare to established normative performance ranges? So we're also interested in whether the interaction between forces based on metrics and velocity-based metrics help explain variability in jump performance across teams. And our hypothesis is that athletes in strength and power-dominated sports, like, for example, basketball and football, show higher propulsive forces and greater jump heights, and where to, like, in contrast to athletes in speed or endurance-focused sports, like soccer and track, they're expected to demonstrate high peak velocities during jump assessments. So overall, we anticipate differences based on each sport's, like, physiological demand. To get into the significance, so basically it matters because when we were looking at the existing research, we noticed that most studies focus on either just one sport, a small group of athletes, or very large controlled lab settings. There's actually very little work that compares these metrics across like multiple different collegiate teams in like a real world testing environment. So that's why our that's what makes our data set so valuable. It's large. It includes repeated measurements and it covers several different sports using both real force plating and GPS systems. So that gives us the chance to explore cross-sport differences in a way that current literature hasn't really addressed in a sense. So we selected these five metrics specifically because they're consistently available across teams in our data set and they're really well supported in sports science research. For example, jump height, which is our main outcome, it reflects the overall lower body performance, and whereas to peak velocity tells us how quickly the athlete is moving at the key moment of the jump. So when we looked at all of our metrics together, they gave us a clear picture of the athlete's um, performance profile, and it let us compare different sports in a meaningful, evidence-based way. And now to Cynthia for the methods.
So for the methods, we began by conducting a data quality assessment for our selected five metrics. And the only metric that we kind of found like no values or zero values for system weight, where they had 78 zero values. And then all teams met the requirement of at least five tests per athlete, which supports like reliable trend analysis. And during our data quality assessment, there was like 829 athletes that had not been tested in this last 6 months. And this is like an important indicator or like a note because for our flag system that will be discussed later in our presentation. And basically, it kind of like the flag system kind of highlights the athletes who may require like follow-ups or additional monitoring. And for our analysis approach, we filter the database to focus only on our five metrics and organize the data for athlete comparison. We also made sure that we had enough data for stability and consistency throughout our analysis. And with all the filter data, we prepared a trend analysis, flagging threshold, and a comparison between athletes that are presented later in our presentation. Next slide. So first off, for our key findings, we have this table that measures the total tests per month by metric. And the metrics are color-coded with a key table on the top right to kind of see like what colors are for which metric. And in the red box, it's showing the data collected from August to April, which is like the typical school year for student athletes. And the purpose of this table is to generally see when is most of our data collected, which can help us know when or like during which time frame is the most reliable during trend analysis and more. Moving on, Rizal will discuss more of our key findings.
So for this slide, player 1239 shows consistent improvement across all neuromuscular metrics with upward or stable trends. The strongest performances occur in late 2024 into early 2025, as seen in the red box on the top right. Because system weight remains stable, these gains represent genuine neuromuscular improvements, and overall, the athlete demonstrates strengthening performance, capacity, and enhanced power output over time. Next slide. Player 691 is an example that shows consistent declines across all neuromuscular metrics. The most significant drop occurred between March and July 2024, which is identified in the red box as well, where performance sharply declined despite a stable system weight, suggesting fatigue or readiness issues. Statistical results confirm that these declines are meaningful, indicating reduced power output and potentially elevated fatigue, injury risk, or inadequate recovery during this period. You go next.
So for some key findings, first athlete 1239 represents the positive end of the performance spectrum, with their trends matching what we see in our lit review around healthy stretch, shortening cycle function, and steady improvements during consistent training. Their neuromuscular metrics improve across season in a way that reflects real adaptation, not just changes in body weight. In contrast, athlete HHA691 aligns with research on neuromuscular fatigue and reduced neural drive. The metrics drop together across multiple months, which is exactly the pattern associated with accumulated load or inadequate recovery. Excuse me. Next slide. And then based on these findings, we developed a simple rule-based flag system to help coaches quickly identify when an athlete may require a further attention, where anyone falling below the set thresholds is flagged as below performance standard. The two performance standards that we used based on our lit review were jump height being below 0.3 meters and peak propulsive force below 1200 newtons. In practice, the flag helps us catch meaningful drops early. For example, sharp declines similar to what we see in athlete 691, which trigger a red flag, prompting coaches to review kind of like their load, recovery, or any other potential stressors. Next. And then this is kind of a like a snippet of our flag system graph. So this snapshot of our flag system graph shows all of the currently flagged athletes along with their team, the specific reason why they were flagged, as well as the most recent metric value and the date of their last test. You'll notice that a lot of the flags are for jump height falling below the 0.3 meter threshold, but we also occasionally catch low peak performance readings. And the table gives coaches a quick department-wide readiness map, and it immediately highlights who may be trending downward or who might need a check-in and where we might need to adjust training loads. Moreover, it's simple and it's easy for coaches to understand. Next.
So continuing on practical applications, implementing an automated flagging system can help coaches and trainers quickly identify underperforming players, and they can adjust training loads when metrics decline, and the system can highlight overperformers who can offer useful insights. And they can also increase testing frequency for more reliable trend detection. And for filling in the literature gap, as mentioned in our introduction, many existing studies use small samples and lab controlled testing, while this project uses real world department level systems that translate data into performance monitoring tools. The flagging system can also highlight how consistent force plate metrics can track individual adaptation over time. Next slide. So getting into limitations of the project, uneven testing frequency across sports teams may cause bias when some athletes have very few measurements, causing limitations on the reliability of trend analysis. And the wide date range of the dataset can cause inconsistencies with potential external factors that influence the data trends. And those external factors can include fatigue, training load, and injury status. For future research purposes, we can implement normalized metrics according to body mass, such as force relative to system weight, for fairer comparison results. And as mentioned before, having an automated flag system can help speed up training plans for individual athletes. And lastly, we can observe data relating to specific sports or positions to have tailored and meaningful performance insights. Thank you for listening to our presentation.
Great job, guys. Golf clap. Sean, maybe you want to kick us off with this one? Any sort of thoughts, feedback?
Sure. Yeah, no, it's great. I think the practical applications are very strong on that. From my brief interaction with the folks over there, they're not looking at a lot of metrics. So the more that, wherever you all are going to be in sort of a project like this, the more you can dive in and show them other things that might be there. That's great. So yeah, that was awesome.
Yeah. Like the idea of the flag system, sort of rules-based engine, what I'd say that might also be helpful for the athletic trainers. So in addition to the sort of coaches or assistant coaches, if it's able to do like you say and kind of pick up on neuromuscular fatigue earlier on, that could be quite helpful, I think, for the AT team or the athletic trainers.
Yeah.
Um,
They're and I know right now they're using flags that are, like I said, less not that they're not based on analyses, but they're kind of just the first rung of stuff that you're going to look at. And so like you all being able to dive down deeper would give them more confidence in flags like this. And wherever you end up working in any sort of environment, that ability to go beyond that first level is going to help people really kind of trust what's coming out of it.
Hmm. Yeah, and to your point, Sean, if they're already doing something like this, they could then also compare and contrast potentially what the students here have put together for that gut check and see if it sort of matches their own internal flag system. And, best scenario, right? That maybe there's like a slight delta where then the students' approach is more sensitive and they're able
Yep.
to catch maybe additional players that they're not otherwise catching.
Yeah. More data is helpful.
Yeah. And with your flag idea, is that then looking at overall sort of data points and what I mean, like a single point in time, or is it aggregating across the complete player history?
Is across the player history is using the most recent data collection. So we
Hmm.
have like it's like on the our tab is called last test date. So it's like
Hmm.
the most recent data collection, and currently the fact system is only measuring jump height and the peak propulsive force.
Hmm.
So I feel like our target towards the FAFSA system was towards like the athletic trainers to kind of come up with a more comprehensive training plan for the athletes to kind of like, like create a plan that's better for the performance or like based on the performance. So that's what we were thinking as well.
Hmm. Great, great. Yeah, yeah. And I think, if they were to see this, it would definitely inspire them to potentially think about doing things slightly different. And then related to the weight metric, that's kind of interesting. A lot of missingness. And Sean, that my question here is for you. I don't know if they're probably just using a good old weight scale or something like that
Yeah.
to measure weight.
Yeah, and I don't know how often they're entering it. It's one of those availability things. I think the primary metrics they're using are AAL, speed, distance run at different speeds, and the VALD readings on the force.
Hmm. Interesting. Yeah. And I think my last comment here is we're now already beginning to see a trend of data consistency and data capture, right? And the impact that that has on the types of questions and your ability to answer those questions. So, one point for all groups here as it relates to next steps and recommendations, I think would be, if you were to come up with a recommendation for data capture for whatever metrics you've identified, what would that look like? So just something to think about because that could certainly be an actionable recommendation that we pass on. All right, great job, guys. Any questions from the rest of the class here? Going once, going twice. Adios. Okay, great job. Group number 7. Let's see, who's our next lucky group going to be? Um, let's go to the top now. Let's go to group number 1. Sadika and Paul's
Yeah.
group.
Briggs, you want to share?
Yeah, can you guys hear me?
Yes.
Okay.
Screen share is, yeah, I could see the web
Can you
browser,
guys
Canva. Yep, cool.
all good?
Yep, feel free
Mm-hmm.
to start whenever.
Yeah. Just wanna make sure everything is in place.
Mm-hmm. Mm.
All right, guys. So we are 5 of us just sharing our analysis on the metrics that we all have been looking at. This is the flow. We know the flow. So we're going to do a structured approach to this. Let's see how it goes. The first thing that we looked at, there are so many metrics and so much data. What is the basic framework that we need to understand and create a interesting inquiry. So we came up with some key words. I'm a fitness enthusiast myself, so we came up with some key words. These were also in the literature review and in the data. So based on these keywords, we came up with a research question, which ties two very important systems in sports performance to how these two systems interact with male and female athletes and their performance metrics. So based on that, we tried to understand as to what's really going on. Our literature review said that RFD, which is the rate of force development, is kind of like an engine, and movement efficiency and gait complexity is kind of like a drive train. So is there a cause and effect relationship there at the very high level? We can go into the weeds all we want, but then what's really happening? So we looked at a lot of data and a lot of literature review, which we will come to later when Jason speaks. But then eventually all this led us to 5 metrics. 2 of them based on force, 3 of them based on movement, efficiency, and gait. So we're trying to understand all of this through this system. Now Paul is going to take over.
Okay. Thank you. Next slide. Okay. So we use Python with pandas in a scalable, reproducible workflow, focusing on project's critical variables for reliable analysis. So the data sets that we have contains about 6 million rows, which about 5 million rows are usable. This includes 548 metrics, though we only focus on 5 metrics, and also this covers 1,287 unique players. Among those 3 devices, Kinexon has the highest contributed share, which has about 4 million records. And from the metrics that we have that we chosen, we did so 88 players, women, and also 111 males players. So we began with the systematic data assessment, identifying missing values, duplicate records, and also formatting inconsistencies that could compromise analysis. Accuracy was validated against logical threshold and the domain-specific rules, so ensuring the dataset is aligned with expected ranges and relationships. Now, to improve the reliability, we applied data cleaning techniques which remove incomplete or duplicate data, or also remove zero values, or also to reduce the noise, normalizing the data to its standard scaling, and filtering also outliers for I'm not done yet. Impact of the extreme values. All procedures were implemented through modular workflow designed to avoid hard coding and also to maintain environment consistency, making process scalable and transparent. Now, for our analysis approach, we do combine it using descriptive statistics with benchmarking and also techniques, using z-scores and also threshold to highlight the deviation from expected performance. To ensure the scalability and also the reproducibility of the workflow, we do structured it to prevent hard coding and also maintain environmental consistency. Since we work with multiple teams, we regrouped them by sports and further separated them by men and women categories. This enables more nuanced comparison, and we examine both team level aggregates and also player level aggregates distributions, capturing broad trends while identifying individual outliers. The results were we presented in a dashboard that translated complex outputs and also clear visuals, making it insights actionable and easy to interpret for diverse audiences. And the key findings will be for Naira.
Hi. Three main key findings. Coupling. The fundamental coupling between two systems, as you see, two system metrics is similar in both genders, but the operating range is shifted upward in males. Second key finding is moderator interaction models testing gender as a moderator of rate of force development demonstrate complexity in relationship. We think that's because in one instance, speed max is higher in female players than male players. And our team thinks that there's something there that meets the eye. The third key finding is relationship between rate of force development complexity and movement gait complexity is positive and consistent. Next slide, please. So as you see in this slide, our key findings become obvious. For example, in the snippet on the bottom, which is from the comparison, speed max in women is slightly higher. Distance total in both gender are similar in female and in male. Next slide, please. Next slide. This slide represents our visualization for all players, women and men. Over to you, Jason.
So from the 4 selected players, we see that, for instance, player 741 is more force dominant. So we could suggest coaches focus on reducing stiffness. But on the other hand, player 555 is more tendon dominant. So we suggest coaches carefully manage the acute to chronic workload ratio. Player 755, again, is the force work capacity or a workhorse. So in this case, we suggest coaches allow neuromuscular recovery, while player 995 is more explosive or reactive, suggesting that for coaches, preserve the current training balance. Next slide, please. So this slide shows the graphical representation of the 5 metrics for all players over a period of 1 year. Next slide, please. So this is the flagging system we use for the selected metrics across our chosen teams, showing low, normal, peak values for each player based on all the work we've done. We then added flagging logic based on a threshold baseline, which flags underperforming players. Initially, we thought of including football, but later removed it, but it is part of our code. Next slide. In case you want to have some fun, we have this slide, which shows the analytical framework defining performance metrics and threshold. Here we see jump height, for instance. The logic is if it decreases greater than 10 to 15% from baseline, it indicates neuromuscular fatigue. While for speed max, if the logic is if it's less than 90% of personal best sprint speed, suggests suboptimal readiness, taper recovery, which is needed. Next slide. So the recommendations are based on our research question. And what we have observed is that coaches can combine tests of rapid force and movement coordination, which is derived from movement efficiency and gait complexity, to better predict and improve performance. Second, correlations enable predictive models and game readiness algorithms for performance prediction. And third, because there are correlation between metrics, it can help examine how empirical data supports multi-domain metrics clustering for performance assessment across sports and sexes. And finally, to reduce the female athlete gap, more focus is needed by collecting data through metrics focused on female players, while also ensuring labeling and filtering of metrics, which are optimized such that it does not create any bias against female athletes. And now on to Siddiqa for limitations.
Some challenges that we faced during this research project was that the data was only collected in selected testing blocks, which can create gaps and inconsistent longitudinal coverage. Also, testing doesn't always occur when the athletes are at true peak readiness, so there was no true baseline values. Missing positional context, lack of positional data limits the understanding of workload variations caused by different team roles. And since different teams in sports use different metric sets and thresholds, this limits direct comparability across sports. So we were limited by our knowledge, data quality, and accuracy. And as far as future work, it should involve the standardization of key workload and performance thresholds across these metrics that we explored. And there needs to be an expanded coverage and studies on female athletes who remain persistently underrepresented in many device-based studies. I'll turn it over to Brooks for the conclusion.
Thank you, guys. So yeah, we went through the whole structure. in the outro, we just like to say, metrics are metrics. You can have n number of metrics, but eventually, when it comes to performance and sports, the technical strategies that we have with each athlete, the organizational strategies that we have in their recovery and in the other planning, those are very important. Of course, metrics are important. And so this was a nice little project that we really enjoyed working on, all of us. Now, if we have any questions, we'll be happy to answer. And just in case somebody has any ideas, that thing that's moving is just a histogram, so don't get ideas.
Nice. All right, great job, guys. So I'll start off with a couple of things here. I liked how you conceptualized and came up with these constructs of RFD and the MEGC. I think also you emphasized the lack in the literature on male versus female, and I think that's something that just needs to be highlighted. And also a potential opportunity for, publications and just to put out sort of work, whether things are correlated or like not correlated. If there isn't a lot known about female athletes because 70+% of what's put out there right now is just about males, it's not really helpful for the female athletes. So I think that there's like a strong case there for getting this type of work, out the door and into the hands of, coaches, regardless of what the sport is. And you guys focused on, was it the four different case studies? It was basketball, and what was the other one again? Sorry.
So we initially we started off with see, again, this is an exploration, right? We have this whole data set and everything. Initially we started off with basketball, men and women,
Mm-hmm.
and football. And before that we had five sports. We just wanted to go what we are interested in. But eventually, after realizing all the things, we were like, okay, basketball men and basketball women, because of the
Mm-hmm.
volume of data, number one. Number two, direct comparability. Number three, the fact that, there is, once we learned that there is this huge gap, only 8.8% of studies from whatever credible data source we found, only 8.8% are women focused. So imagine, only men is about 70 plus, men and women both is the rest, only 8.8. So 91.2% is including men in the studies. So that's very, very interesting.
Mm-hmm. And maybe Sean, you could sort of jump in here, right? So we have female basketball, female soccer, we've got females in track and field, swim,
Lacrosse.
Cross.
lacrosse. Yeah.
The one thing we
Softball.
did see very interesting was, the 92 team names. So I don't know, you were messing with us, Hans, or is it actually
No,
the
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 wild, wild west out there?
yeah, so I've seen what happens like every time they create a new group inside of the platform, it relabels it. So when you saw that, I have a whole Google sheet that's actually running live, telling me whenever there's a new team name and what I need to make it actually show up as.
You
So
know,
yeah,
I did, I'm not a coder, but then yeah, I was doing some stuff on Google Colab. Firstly, connecting to the server on Google Colab is a mess. So I found a JavaScript to keep hitting that click thing so that it keeps connected to this to the database. Otherwise, it gets disconnected after a while. Tried using fuzzy logic and other things.
Mhm.
Somehow I could not. I'm not a expert coder, so I won't even say that. Okay, I'll be able to do it. I tried, but then yeah, those names. Oh my God! At least
yeah,
in the end, after we cleaned up for the metrics, we found 32 unique teams. And from that, we just so kind of made some kind of sense, because this is a really, really wild thing that we have here.
Yeah, I
And
think there should only be like 10 to 13 teams. I forget what the
yeah,
number is off the top of my head.
unfortunately, I was just looking up the Stony Brook Sports Athletes website and all. The women's teams doesn't seem to be doing that good. I think they just lost the last
So
couple of games. So yeah.
yeah, so like I think what would need to be, like maybe this is for a future discussion, but in terms of just focusing, Sean, on our female teams could be quite interesting. Or again,
yeah,
obviously we want to focus on everybody, but it's an interesting gap that, especially if then the coaches, the trainers, the performance staff, right? they're then kind of dealing with like a deficit versus we know that there's like a lot of normative ranges for the males. But anyway, and then just one last quick thought. Um, in terms of the visualizations, I think what would also be helpful for your final sort of visuals, just to throw in one that I like the, time series and the sort of, showing all of the different metrics on some of the same slides, but then maybe averaging the metrics across male versus female. So then you're not showing all individual players as unique lines. And could also potentially thinking about sort of just averaging from a time series perspective, maybe just a couple data points. And by that, I mean, instead of looking at like date timestamps, you kind of look at for a particular season, their like first, second, third, fourth, fifth data collection points. So then instead of say, looking at dates, you're looking at counts of progression of the data collection. It might help kind of cleaning things up. I
Yeah,
think,
yeah.
the again those charts are still informative, but
Mm,
if we were to like scroll back over to them, right? If you have too many lines, too many things going on, kind of
mm.
hard to sort of discern what's actually happening.
Yeah, the one quick response that I'll have for that is so, like in this slide that we have so much stuff going on. So, what basically we can also see that there are the the uh, the the pattern that we see is, yeah, there are definitely some gaps in, maybe it's the summer or whatever. So the lot of consistencies once we take out the outliers. There's a lot of consistency in the data that is being captured after we reduce the outliers. And for the data visualization, we have this Streamlit app. So yeah, we'll connect offline, and whatever you
Mhm.
need, we can just add stuff here. So it's not a big tweak, but we'll just add stuff here, because here we can go through different players. Like this is just the players that we selected. We can just uncheck it. It'll go to all players, and we can do it gender wise as well.
Mhm.
So it'll be a fun little
Okay.
project.
All right. Great. Anybody else want to chime in? Ask any questions or other thoughts?
Gonna
Okay,
say
let's
not.
move. Oh,
Oh,
sorry.
sorry. The
Yeah, yeah.
teams are not all gender centric. Is like it's only one basketball team. There's only one volleyball, so we weren't sure.
No,
No,
no.
there's
What?
one of each.
Is it
Yeah.
one of
Mm.
each?
What we did on our we did change in the coding that if the team would have a male and it
Hmm.
will become, and it has a sports also, it will become male basketball, then female basketball, and if
Got
there's
it.
like,
Okay. So
you
you
know, it,
you switched you switched it
yeah, we
even
just
though the
generalize
team.
everything instead of
Got
like
it.
having per team.
Got it. Okay. Thank you.
Awesome, guys. I hope you guys had fun. Thanks.
Hmm. Good
Han,
question.
should I show the back end on our side?
Yeah, sure. Yeah.
Today we will be presenting the insights that our team found by analyzing Stony Brook University's athletics database containing performance metrics collected from multiple systems, including Hawkins, Kenexon, and Feld. This project challenged us to extract insights from health and performance data using Python and SQL, applying real analytics to understand athlete performance. Next slide, please. So this is our table of contents. So I will be going over the introduction, and then Patrick will go over the method section, and then we have the key findings, practical applications, limitations, and questions at the end. So I will begin talking about the research question. So our research question was, to what extent do average braking power, average propulsive power, and the durations of both the braking and propulsive phases predict jump height in basketball athletes? So our hypothesis is that jump height in basketball athletes is positively influenced by average propulsive power and negatively influenced by average braking power and the duration of the braking phase, with propulsive phase duration also contributing. So in short, athletes who generate higher propulsive power and efficiently manage braking power will achieve greater jump heights.
Next slide, please. So these are the metrics that were chosen because they collectively describe both the power output and movement efficiency involved in jumping, which are key to basketball performance. Next slide, please. So what research gap are we trying to address? So a key gap in current literature is the lack of standardized methods for calculating jump height, with different approaches often yielding inconsistent results. These inconsistencies make it difficult to determine how braking force, propulsive force, braking phase, and propulsive phase units can be used to predict jump height. So by analyzing real athlete data using consistent metrics, we hope to better understand which factors most strongly influence jump height and provide insights for training and injury prevention. Now I'll pass it along to Patrick.
All right, I'm going to be going over the methods section, which included data overview and our analysis approach. So for data overview, we used the data obtained by Stony Brook Athletics, and all of our metrics came via Hawkins technology. There was a large amount of data for all of our metrics, with the minimum being 32,107 across all teams for average braking force. On top of this, there was sufficient data for both men's and women's basketball, as these two teams were frequently tested using Hawkins. We didn't identify any null values in the long format for any of our metrics, and there were outliers identified and excluded when necessary. We used only metrics within the interquartile range from 25 to 75%. And here's the example of finding no null values throughout our data. And also just an obvious case of an outlier being 14,885 meters in the air. I don't think anyone's jumping that high. All right, and then as for analysis performed, we found the means for all of our metrics for both the men's and women's basketball teams. And then we performed a t-test to compare the means of all metrics between men's and women's basketball, as well as the p-value to see if there's a statistical significance between men's and women's. And finally, we used R-squared values and scatter plots to test and visualize correlations between the four metrics and jump height. And here's an example of the code that we used to obtain our statistics. I'm going to pass it off to Emily.
Okay, so now we're going to be talking about the key findings. We conducted a statistical analysis using the methods that Patrick mentioned to compare the men's and women's basketball teams and understand what kind of impact the metrics we chose drove like jump height performance. Next slide, please. So here to start, we can see that we have our t-test results comparing men's and women's basketball, which revealed some interesting differences across the metrics that we've chose. Men's basketball athletes jumped substantially higher at about 42 centimeters compared to 22 centimeters to women. And that's about like a 43% difference in jump height. Then looking at the force reduction, men generated more force significantly across the board with, as you can see, 1,722 newtons versus 1,346 newtons for braking force and propulsive force. With braking force, and then for propulsive force, 1,967 compared to 1,490. As you can see, the p-values for all of these metrics were pretty significant, except for the braking phase and the propulsive phase. Those did not have any really significant p-values. They were all below our significance threshold of 0.05, and they were also with very, very similar. So we could see with this that there wasn't too much of a significant impact from the propulsive phase and the braking phase. It was more so the forces. Next slide, please. Here we visualized the box plots for comparing the men's basketball teams and the women's basketball teams, like across the metrics. So this is basically just what I previously discussed about the statistics. We can see here that the jump height was pretty different, and the men's has more variation in comparison to the women's. Next slide, please. And then here we have for the rest of the metrics, here we can see again that the propulsive phase and the braking phase were essentially equal. And the average propulsive force and average braking force had more significant difference between the two. Next slide, please. So now I'm going to be going over our scatter plots. we have three scatter plot visualizations. This one is measuring is comparing the metrics across all teams, like all of the basketball teams or athletes, sorry, my bad. And here we can see that for the combined data from both teams, the propulsive force showed the strongest correlation with jump height with an R squared of 0.477. And that is even though it's not close to one, it's still significantly higher than the braking phase and propulsive phase. So it was pretty significant for our findings. But the critical finding that challenges common assumptions about jump training. The time metrics show virtually no correlation, and the braking phase had an R squared of 0.03. So this kind of meant that we didn't. No, sorry, Patrick, you can switch it. It's kind of meant that it didn't matter how long it took to execute the jump. What mattered more was the force. Here with the men's scatter plot, we can just see a similar trend in the propulsive force and braking force, similar to the all-around teams. And same thing happened to the women's basketball scatter plots. Now we can move on to the next one. Okay. To summarize it, we can see that the force production, not the movement speed, is the primary predictor of jump height, with the R squared values being between 3.4 to 0.48 versus 0.01 for the timing metrics. And then we can also see that the men generated significantly more force than women across both force metrics, which kind of lines up with the research that we've been finding about gender differences being pretty significant for force production. And we can also see that from a training perspective, the duration of the propulsive phase and braking phase showed no meaningful impact on jump height performance. And the timing of the metrics did not differ significantly between male and female athletes in comparison to the force metrics. And now I can pass it off to Avion.
Okay, so I'll be doing the practical applications. Next slide, please. So after analyzing all of our metrics, we wanted a way to turn this huge data set into something that coaches can actually use day to day. And that's where our flagging system comes in. So the idea is kind of simple. We want to automatically identify athletes who might need more attention, either because their performance is dropping, because they're testing less frequently, or because they're lagging behind their team averages. So our system uses three main checks. And the first one is our performance decline. So essentially we look at their baseline and flag them if their values drop more than 10%. This helps us catch early signs of decreased power fatigue, injury risk, or inconsistency. And then the second one, we have team comparison. So essentially, if someone is more than 1.5 standard deviations below the team for a metric, we flag that too. And this makes sure that we aren't missing any athletes who may be consistently lower than their peers, or even their own baseline hasn't changed. And finally, we have testing frequency. So essentially, we just check that if they haven't been tested within 30 days, they get flagged. This helps coaches maintain consistent monitoring, because gaps in testings can hide issues. And once all these three checks run, we combine them to create one red flag output file, listing every athlete who needs attention based on any of these criterias. And yeah, this basically gives coaches a quick automated summary, so they don't have to dig through thousands of rows of data, and they can instantly know who may need a new technique review, or who may need adjusted trading loads, or who may simply just need to be tested more often. And we also have some suggestions, which is we could probably maximize propulsive and braking force training. That could probably increase the jumping performance of athletes. And we could definitely prioritize consistency in teaching schedules across the season. Next slide.
So now that we've talked through the main findings and visualizations, I'm going to be discussing some of the limitations of our analysis and what future work could potentially look like. Next slide, please. So to begin with the challenges, the data set was extremely large and complex. So since there's so many variables per athlete to consider, it takes time to understand what each metric actually represents and how they were calculated. Athletes were also tested at very different frequencies. Some athletes had hundreds of sessions while others had quite a few. This even uneven distribution made comparisons more difficult and required more careful filtering. We also lacked information about certain testing conditions. For example, if jumps were done pre-practice, post-practice, if they were fatigued, or doing things under specific protocols. So without that context, some of the variability in the charts could be more difficult to interpret. And next slide, please. Now going on to the limitations, there's also an inconsistency in how jump height could be calculated. Different sessions could have different formulas or equipment, which could again affect comparability. There's also an uneven data across teams. The women's and men's teams didn't have the same amount of testing, so this could limit how confidently you can generalize team-to-team comparisons. And we also can't control for athlete contact. So things like fatigue, injury, or strength training phases, these factors can influence performance, but aren't reflected necessarily anywhere in the data set. And then finally, our work is also correlational. So we can identify patterns and relationships based on our results, but we can't directly claim that one variable directly causes changes in another. And in terms of our future work, there are several areas where this project could be expanded. So we can start with collecting more balanced data, so both across athletes and teams. So that way it can make comparisons stronger and more reliable. We can also monitor athletes over time, which would allow us to study individual performance trends and not just like session level snapshots. There's also a lot of potential for predictive modeling. So with a richer data set, we can also try to learn to build more machine learning models, which could maybe predict jump performance or even flag abnormal results that may indicate fatigue or injury risk. And then we can finally also explore gender-based differences in more depth. So our charts, even though show statistical differences, understanding why those differences exist would also require additional analysis. And then we just have our references, and that is all. Thank you.
Awesome. Good job, guys. Like how you selected basketball, kind of focused on metric related to something that's a little bit more sport specific. Might still be able to expand this to a couple other sports, like for the track and field, the long jumpers and things like that, perhaps. Um, good job picking up the outlier of 14. You said it was 14,000 meters?
14,800, I think, yeah.
Yeah. Obviously that person did not jump that high. I'm kind of curious. I wonder sort of how that happened. Maybe it's like the
It looked like it was
machine
a
got
test to
goofy.
someone. It was like Stony Brook Athletics, so I'm assuming it might have been a test, but
They
I don't know.
like threw up in the air or something
Yeah.
and had somebody catch it, that kind of thing.
Yeah. Um, it sounds like you guys have picked up on some similar points that Group 1 picked up on as it relates to the lack of standardization for female metrics. Um, like your flagging ideas, like with some of the other groups have done. And then you mentioned like baseline. For any group that's doing or creating a baseline, one of the questions that you'll get is how are you defining or operationalizing a baseline, right? Even though we imagine baseline means some type of first point in time, but that could still be um, defined in a variety of different ways if you get where I'm going there. So with your baselines, were you like how were you defining or thinking about defining baselines? So was like baseline like as an example. And if you don't have the answer to this now, right, it's perfectly fine. Something to think about. Is baseline like the first data point for that individual for a particular year or season, or is it their first ever time point for a particular metric, or is it something else?
I think the baseline was based off of an average of like the team as a whole and then breaking it down by athletes and
Mhm.
finding their averages. And then we kind of based off their averages. If they're below their average from a certain time period, then it would be flagged.
Got it. So it's kind of like a moving average baseline where it's based on a team average. Okay, cool. Yeah, and again, not necessarily any right or wrong ways of like, doing things there or defining them. And I'm sure Sean can sort of chime in there that it's really up to whoever is, utilizing that data to help define some of these concepts that might be more, loose, abstract concepts.
Yeah. Sorry, my thoughts for this one were slightly in a different spot, but yeah, that's an interesting idea. What I was thinking, and sorry for going on tangent, Hans,
No, do it.
one of the most important things in any of these, and you all have done a great job of this so far, is explaining limitations. I really this one in particular, understanding that you all are looking at these data and someone is going to see a chart and go, "Ooh, correlation, I like this. Awesome. Like this means something." And you say, "Well, no, because what if we did this in practice and before practice and after?" Like that understanding was really, really good, and I think really important when you all do get to the kind of the end of these things and the so whats and all that stuff on being able to communicate to folks that it may say something, but we really need to make sure we're contextualizing everything. And that's where collecting more of these data points with those additional information points will be very, very helpful. So that was a really, really solid understanding of what those potential limitations could be. I really thought that was great.
Mhm. Yeah, Briggs, you want to chime in?
Yeah, so what we found was, there are almost 5,904 rows with uh, unknown team values. So God knows how many athletes that represents. Then there were about 1 million rows that did not have proper value in the value column, like non-zero values. So yeah, as Sean just said, the coming from finance world, data is data. You can work it whichever way. But then, yeah, having the right logic, like we talked about baseline, we worked off from not only a logic from a statistical point of view, but we also looked at NCAA baselines and thresholds, what's out there in the literature, especially the latest, the last 3 years. And then we decided as to what, as a team, what we'll work with, and we created a flag system like that. But
Mhm.
yeah, great job, guys.
Okay, awesome. Yeah, really, really nice. Again, I think each of your presentations, are, strong in a variety of different ways, like what Sean's saying. You're all picking up on different nuances. Okay, let's now move to maybe group number 8, the final group, but not the final presentation here. All right, we can see your screen. Begin whenever you are ready.
Hey everybody, my name is Jonathan Trifari. Title of our presentation is Detecting Neuromuscular Fatigue, a comparative CMJ analysis in NCAA men's basketball. So CMJ stands for counter movement jump. It's one of the most widely used tests in sports science to assess an athlete's lower body power, neuromuscular readiness, and fatigue status. And what it is essentially a vertical jump where the athlete quickly dips downward before jumping upward. Um, Moving to the next slide. The introduction here covers fatigue monitoring using CMJ metrics. I'll also cover the research question, the hypothesis, why it matters, and our selected metrics, along with rationale regarding sensitivity. Next slide, please. So today I'm introducing our core research question. We wanted to compare MRSI, the Modified Reactive Strength Index, which is a process-based metric that reflects how the jump is performed, with two standard output metrics, jump height and propulsive net impulse. Propulsive net impulse is the total force an athlete produces over the time they push off the ground during a jump. Our goal was to understand which of these metrics actually changes when an athlete becomes fatigued over the season. Questions like, does MRSI show earlier warning signs, or do the output measures respond just as sensitively? This question will set the foundation for why we analyze these metrics in the first place. Next slide. So our hypothesis is that the MRSI will show earlier and more frequent drops from baseline compared to jump height or propulsive net impulse. Because MRSI reflects how the jump is performed, we expect it to pick up small declines in neuromuscular readiness before output metrics start to change. In other words, we believe MRSI will act as a more sensitive early warning indicator of fatigue, and our analysis tests whether that holds true in real athlete data. Next slide. So why this matters, the critical gap. So this question matters because coaches often rely on output metrics like jump height, but those can stay stable even when athletes are actually fatigued. An athlete may maintain their jump height while their movement quality is getting worse. So MRSI captures the process of the jump, so it may react earlier to neuromuscular strain. The gap is that very few studies track these metrics across a full NCAA season. Most research is short term. So our project helps fill that gap by looking at season-long behavior of process-based versus output-based metrics in Division I men's basketball players to see which one truly detects fatigue earlier. Next slide, please. So here are three CMJ metrics, and we selected and why. We chose MRSI because it reflects how the jump is performed and is known to react earlier to changes in neuromuscular fatigue. We included jump height because it's the most established output metric and is very reliable, even though athletes can sometimes maintain it when they're fatigued, as stated earlier. And we added propulsive net impulse because it captures total force over time during the push-off, giving us deeper insight into mechanical output. Together, these metrics let us compare a process-based indicator like MRSI with traditional output metrics to see which one detects fatigue earliest. Next slide.
Right. So now we're up to methods. So for our methods, we analyzed a longitudinal NCAA CMJ data set collected across multiple teams and seasons from 2018 to 2025. The athletes completed repeated jump tests over time, which allows us to focus on within athlete changes rather than isolated test outcomes. And since this is a real world monitoring data, testing frequency varied across athletes and across the season. So given the variability in the testing frequency and the presence of missing data, especially for propulsive net impulse, the data quality and pre-processing was really important. So to address this, all the metrics were normalized to athlete-specific baselines. And the performance was evaluated as a relative change over time rather than an absolute value. Incomplete or invalid trials were removed and missing data were acknowledged rather than forcing a complete case analysis, which would have excluded a large portion of the data set. Right here in this figure, it shows the total tests collected per month over time, highlighting the periods of higher and lower data densities across the study window. So as you can see, every May of every year, it shows lackluster data. So for our analysis approach, we applied a threshold-based evaluation framework to identify meaningful deviations from the baseline. Thresholds were selected to exceed typical measurement errors or reflect clinical relevant changes reported in prior monitoring literature. So we have three threshold rationales. MRSI is equal to or greater than a 10% drop from baseline, which is our fatigue indicator. MRSI is greater than a 15% deviation from the team average, which raises a team outlier flag. And finally, the jump height and propulsive net impulse were flagged if they were equal to or greater than a 7% drop from baseline. This approach allows us to translate continuous performance data into interpretable fatigue signals, which later informs our practical flagging system. And with that, I'll pass it on to key findings.
Okay, so when we applied our evidence-based thresholds across more than 50,000 CMJ tests, we identified over 18,000 instances where athletes showed signs of neuromuscular fatigue. And what stood out to us was that 2/3 of these fatigue plan flags, which was about 12,000 cases, came out from team-adjusted MSRI, not jump height. When we look at the smooth trends over the season in the graph, we see that MRSI fluctuates much more sharply, especially during known high load periods, while jump height stays relatively stable and often remains within a baseline tolerance. This supports what the literature says that output metrics don't shift until fatigue becomes severe, whereas MRSI captures earlier, more subtle neuromuscular changes. In other words, the athletes that we took tests on were showing meaningful declines in MRSI, even when their jump height looked somewhat normal. And then taken together, these findings reinforce the idea that MRSI is a much more sensitive marker for neuromuscular readiness that aligns well with previous research showings that counter movement strategy variables respond earlier to fatigue than performance outcomes. Next slide, please. And then so across the season, we saw a really clear pattern between MRSI and jump height. What stood out was also that MRSI was almost always the first metric to change. It dropped very early, even on weeks where jump height looked normal. That lines up with the literature that showed that MRSI is a more sensitive neuromuscular fatigue and tends to react to smaller disruptions in stretch shortening cycle efficiency. Later in the season, we also saw that there was reduction in jump height, but they were much larger in much more larger magnitudes. When both MRSI and jump height declined together, that usually indicated a much more global fatigue state rather than just a technical or efficiency issue. So finally, when the pattern supports using these metrics together, MRSI works like an early stage detector, whereas while jump height acts more like a late stage fatigue indicator. This reinforces what previous researchers have found and highlights why relying on one of these output metrics can miss early warning signs. Next slide.
So this literature confirmation and extension, our results strongly confirm what Sukamel and colleague established in 2015, that time-sensitive variables like MRSI are more responsive to neuromuscular changes than output-only metrics. We've extended this work, obviously. Previous MRSI research usually examined single teams over a 6 to 16th period. Obviously, we had a lot more data to work with here. This scale allows us to see seasonal patterns and multi-sport consistencies that shorter studies simply could not capture. Our literature review identified a critical gap. We knew MRSI theoretically should have been useful for monitoring fatigue. There was limited evidence on how it actually behaves relative to traditional metrics across competitive seasons and applied settings. We've directly addressed this by demonstrating that MRSI consistently detects early neuromuscular changes while jump height remains stable, then showing that jump height declines occur later with greater magnitude. This validates that efficiency-based and output-based metrics provide complementary, not redundant information. MRSI captures how athletes move, and jump height captures what they achieve. Most importantly, we've bridged the research to practice gap. We didn't just describe changes, we created an evidence-based threshold driven flagging system using the data that exceeds normal measurement variability. This translates laboratory findings into actionable monitoring protocols that strength coaches and can implement indefinitely, moving the field from descriptive analysis towards practical intervention systems. And next slide, please.
So for practical applications, so with the data that we analyzed and identifying thresholds for flagging athletes' performances, we were able to translate this science into like a simple, practical tool for training use. So we came up with the performance traffic light system. Here's a visual that clearly shows our flagging system. It's a fast visual way for coaches and athletes to make immediate and informed decisions about the training based on their readiness metrics and deviation from individual athletes' baselines. So as like a refresher, our thresholds, we had four of them originally. So first one being MRSI baseline drop, which is flagging when an athlete's MRSI drops 10% or greater below their personal baseline. Second was actually similar, but MRSI with team deviation. So when it flags an athlete because their MRSI deviates 15% or greater from the team's average. And then the third being jump height baseline drop when the jump height drops greater than 7% below the personal baseline. And something that we had to omit was actually propulsive net impulse baseline drop, which was when it flags when the PNI drops greater than 7% below personal baseline. But as we'll explain a little bit later in the presentation with the limitations, we had to omit that because we didn't have enough data. So with that, first we have the green light, which is the optimal scenario. It lets us know that there's normal MRSI and normal jump height, meaning that this athlete is displaying both high quality of movement and high mechanical output. So they're not really showing any signs of neuromuscular fatigue and are not compensating for past loads. So they're ready for full training and they're able to perform at their full capacity. And we can proceed with planned high intensity or high volume sessions. And below this is yellow. This is where the coach needs to be more vigilant with the athletes. Here we see low MRSI, but the athlete is still able to produce normal jump height. So this is a key sign of a compensating athlete because they're showing signs of fatigue where their movement quality defined through MRSI is dropping, but they're pushing through to try to maintain their performance output. So this is a common precursor to injury or severe fatigue drop. This is just a warning, and it means that the athlete needs to dial back on the volume or intensity of training, but maintain the quality of the work. And we need to reduce the load to allow for recovery before a true drop-off occurs, which would be the red light. And this is like a clear stop line where we need to visualize and see that the athlete is having low MRSI and low jump height, which signals global fatigue, meaning the athlete has exhausted their ability to compensate, and both the quality and the quantity of their performance is suffering. And continuing to train at this point is counterproductive and dangerous, and the athlete requires proper recovery. So we should switch to active recovery, light mobility, or a complete rest to ensure that they can fully reset before returning to demanding training. Next slide, please. So how this affects coaches and trainers, the system helps us detect fatigue much earlier and more accurately than traditional methods. It helps us to answer the most critical question of, is this athlete ready to train and how should we train them? Specifically for coaches and trainers, this provides actionable, individualized guidance based on clear metric patterns. Rather than guessing, you get an immediate decision based on the three colors that we just described. This ensures that you're optimizing individual load management so every athlete can contribute their best performance to the team. And by implementing this flagging system and testing athletes ideally every 1 to 2 weeks throughout the entire season, coaches can gain longitudinal data, and this allows them to identify patterns and understand precisely which training or recovery methods successfully transition an athlete from a red or yellow status back to green, creating an evidence-based performance.
So I'll be going into limitations and future directions from here. Next slide, please. So our analysis faced several data limitations. First and foremost, propulsive net impulse was lost during data cleaning, kind of restricting our comparison to just MRSI and jump height when we originally intended to examine those three metrics. And secondly, testing frequency varied considerably. Some athletes, obviously, like Sean mentioned before, tested weekly, while others may have tested monthly, maybe just due to forgetting these kind of machines on the bus or whatever, which may have affected the team average calculations, especially later in the monitoring period when fewer calculations or fewer observations were available. Most critically, we lacked contextual evidence about why these fatigue patterns occurred. We could see MRSI declining, but we didn't have the training load data, competition schedules, travel demands, or subjective wellness measures to kind of explain what caused these declines. We also couldn't validate the practical significance of the flags while we identified 18,971 instances. where athletes met fatigue criteria. We have no injury outcome data to determine whether or not the flagged athletes actually had higher injury rates or performance decrements in subsequent competitions. This limits our ability to kind of learn or to claim that early intervention based on these flags would actually improve these athletes' outcomes. Additionally, our aggregate analysis across all sports mask important sport-specific or position-specific patterns. For example, a linebacker's fatigue signature may differ from a point guard's, but we couldn't examine those nuances with the current approach. Next slide, please. And moving forward, I think the most impactful next step would be integrating training load and competition exposure data to understand what drives MRSI changes. If it's accumulated volume, high intensity sessions, competition density, or inadequate recovery. Equally important is linking our flags to actual outcomes. Do athletes flagged for low MRSI have higher injury rates in the following 2 to 4 weeks? This validation would transform our monitoring system from descriptive to truly predictive in a sense. And finally, breaking down the analysis by sport and position would also reveal whether or not these athletes require different thresholds or certain positions are more susceptible to specific fatigue patterns. These additions could help move us from identifying fatigue to understanding causes and consequences, enabling personalized athlete monitoring. And that is our presentation. Thank you.
All right, nice work, guys. Sean, you want to kick us off with any thoughts you have?
Yeah. So I think that what I was really tracking with on this one too was just the level of action that can be taken from this if it's all put together, right? Like it's very simple. Like a lot of stuff that I end up working on is the simpler the better, right? So when you have those three lights, but with what they really mean and the plan that can be implemented with it, that's great. And so, a lot of you guys have done the keep it simple, and provide those high level things, but I particularly, enjoyed that overview of what the flag system really meant. I think you guys put a lot of thought into like what each level would be, and that was really good. Yeah, I mean, a lot of these I'm seeing as just pick it up, and when you have that additional context from the other folks, pick it up, drop it over there, and they would love that. I think, like you said, you don't know the context about whether or not they were traveling that day or the games or things like that, but that stuff is something that's pretty easy to throw in there. This is great.
Mhm. Yeah, I was going to say some of the same things that Sean said, like Vinny, the athletic performance director, he's also created something very similar, kind of like to your red light, green light system. So you're definitely on the right track there. And I think you would definitely enjoy seeing what you guys have come up with. And you guys also kind of had a slightly different, but not a wrong by any means definition of baseline, right? We were talking about with the previous group where their baseline was being defined at like the sort of group level versus you were then defining baseline at the individual level. But one really interesting point that I thought you brought up that would be fascinating to look at later is you were then also looking at some of these at the team level. It sounds like sort of determining at a team level how well is that team performing. So kind of taking it through a different, I guess, perspective or level of analysis there, focusing on the overall team performance versus an individual performance, which is I don't know if we currently show that type of level, Sean, within any of the existing dashboards, or if they're all mostly player
Um,
specific.
I have average team performance, but it's only one chart, and it's for AAL. Just
Hmm.
kind of looking at it, it really does kind of show when they have a game and when they don't. That's really
Hmm.
what it does show.
Because then they're kicking it into overdrive. Yeah.
Yeah, yeah. I mean, you can, especially on the football side, because that was the one where it skyrockets on game day.
Hmm. Yeah. Awesome. Yeah, overall, again, great job there, guys. So next group up, let's move on to, we got three more groups. Let's move on to group number 4.
Okay.
All right, perfect. We could see your screen. Feel free to begin whenever.
Okay, so our group will be presenting our sports analytical project focused on injury risk among college basketball athletes. Our guiding research question was, how does gender influence injury risk in basketball players with high asymmetry and high training loads? We formed the hypothesis that female athletes may be more susceptible to injury when exposed to high levels of asymmetry or severe training loads due to differences in movement patterns, biomechanics, and strength profiles. This question matters because injury prevention models often only use broad thresholds that don't always capture individual athlete risk. If standard combined risk criteria fail to identify high-risk players, then coaches may need more personalized approaches instead of relying on generic rules. In basketball, athletes face repetitive loading, rapid deceleration, and unilateral movements such as cutting, pivoting, or jumping off one leg. These demands place stress on the musculoskeletal system and can contribute to injury risk. Research showed that asymmetry, particularly left and right strength imbalances, is linked to ACL tears and ankle sprains. Even small differences in limb strength can alter mechanics and increase stability. Similarly, accumulated acceleration load, the total stress an athlete experiences across practices and games, is associated with overuse injuries and fatigue. When training loads spike too high, athletes may be at a greater risk of muscle strains or stress factors. For our project, we focused on two main metrics: asymmetry with a threshold of 10% based on clinical literature, and acceleration load accumulation derived from Kaizen sensors with a threshold set at the 90th percentile of our sample. Together, these two metrics capture both structural imbalance and overload risk. And now my group will present on the methods.
So for our analysis, we worked with the SBO Athletic Database, which comprised of a total of 1,287 athletes across 92 teams. For our specific focused on the college basketball players, it gave us 183 distinct players split between male and female teams. But when we did the query, it gave us 214 rows that fell into the risk categorization. So we used the 214 rows instead of the 183. We collected data from two primary sources. One was the Kinexon sensors, which tracked accumulated acceleration load. And then the Vlad force plates measured the left and right max force. Our first injury risk metric was AAL. And this metric captures the cumulative stress placed on the athlete's body through the X, Y, and Z axis, which is the speed, impact, and jump. We use the 90th percentile as our threshold because research shows that excessive loading beyond this point is linked to injury risk. And then we have the second metric, which was left-right limb asymmetry. We calculated forces asymmetry using the formula of the difference between strong and weak limb divided by the strong limb, and then multiplying it by 100%. So this gives us a percentage that represents how imbalanced an athlete's force production is between the left and right limbs. So in our case, because we're talking about basketball, we're focusing on the left and right legs. We used a 10% threshold because this value is well established in the literature as clinically significant. So anything above 10% means asymmetry in the limbs. For our analysis, we separated all 214 players into 4 distinct groups. And we also did a separation between the female and male players. The first group was basically no risk. So they had load, AAL, and low asymmetry. The second group had high load and low asymmetry. The third group had low load and high asymmetry. And then the fourth group had both a high load and high asymmetry, which was the highest risk group.
Okay, so next I'll be talking about the key finding. First thing first, you see the basketball players classified in risk categories. There's a total of 214, and then it's greater than the total distinct basketball player of 183 because there could be multiple player on the the player could appear on the same team, like on multiple teams, and they could performing different season. And then the 161 is a basketball player who have at least one of the three risk-related metrics. So that's either left, right force, or acceleration. And then basketball player with all three metrics is only 34. So players classify as low risk when they do not meet either of the two risk condition. So like their balanced bilateral force asymmetry is less than 10%, and their moderate training load is below the 90th percentile. However, this classification is limited to the metrics available, and it does not account for other injury risk factor. So it's important to know that low risk, it does not mean no risk. It just means that they didn't trigger a specific threshold. One more thing to keep in mind is that player with missing data, so like they don't have a left-right force or no accelerated load data, they also fall into a low risk category because they can't be flagged. Next in the graph, you see an equal number of male and female player, 10 each, that shows high bilateral asymmetry. It means that their left-right forces difference is greater than or equal to 10%. However, given the smaller female sample size, this represents a slightly higher prevalence in female, which is 11%, compared to the male's 8.1%. These players may benefit from like a targeted unilateral strength training to address like the imbalance. Next, for the high load player, or those who are top 10% of the accumulated acceleration load, they represent the athlete with very high cumulative training demands. So in our basketball sample, there's 6 females, or 6.6% of the female sample size, and 12 male, which is 9.8% of the male sample size that met this threshold. This can suggest that male may be exposed to a slightly higher workload, though the difference was not statistically significant. These players may benefit from load monitoring and periodized training to reduce overuse of injury risk. Lastly, the combined risk are players who met both conditions, so they have high loads and high asymmetry simultaneously. And from the chart, you can see that 0 player in the basketball sample met both criteria. A positive way to interpret this data is the absence of combined risk suggests that athletes with high asymmetry are not simultaneously accumulating high excess training load, which may indicate that effective load management or self-regulation. And player with imbalances may naturally modify their activity level, or coaching staff may be monitoring and adjusting workflow for these specific athletes. While a more cautious view may indicate that combined risk was rare, and this may be resulted from that our threshold was being too conservative, so like 10% or like the 90% percentile, or like our sample size was just too small and it limited detection. However, it's so important to keep in mind that those 20 players that showed isolated asymmetry and the 18 players showing isolated high load, they warranting continued monitoring of both factors independently. And then this slide just shows the average means of male and female basketball metrics for accumulation load and asymmetry percentile. So what we get away from this specific data is that female shows slightly higher mean accumulated acceleration load. So that's 417 versus male 392, suggesting they might experience a higher cumulative neuromuscular stress on average. And then female also shows slightly higher mean asymmetry, 4.58% versus male 4.03%, though both gender are well below the 10% clinical threshold. And then standard deviation are large relative to mean, indicating high variability within each gender group. Next.
Okay, I'll be talking about the practical application. So we created a performance flag, and as you can see from the previous graph, right, no athlete showed combined risk code. That shows there might be excellent load management. The strength training programs are actually preventing that overlap, or we just don't have enough data and the metrics are not right for this criteria. So the green flag, the criteria we chose was asymmetry less than 10% and load less than below the 90th percentile. So this shows athletes who are in low risk, right? And then yellow flag shows just one risk factor, right? Either asymmetry is greater or equal to 10%, or is a big part of this. Load is above the 90th percentile. So like Joe talked about recommendations in this area for the yellow flag relating to asymmetry, maybe coaches should start incorporating unilateral strength training, evaluate performances, maybe including plyometrics, and then maybe testing again 2 to 4 weeks. And then for the yellow flag associated or related to load, just observe weaknesses in athletes that show like more heavy load, and check maybe to see if these loads are not being underreported or underrepresented. Like we said, the data might be missing as well. And for the red flag, this is critical risk. So both asymmetry is greater than or equal to 10%, and the load is above the 90th percentile. So like our data shows, there's no combined risk showing. So this might just need predictive monitoring just to continue monitoring these athletes. So for recommendations, I already talked about the unilateral movement patterns, watch for load increases. And another important one is to keep an eye on transitions, right? For these sports, they go home, for winter, for summer, some of them, they have summer packets, right, to go continue workouts, but some of them, they might not do that, or they just, they don't have that strength anymore. So when they come back, they're these strength deficits. So getting them back on that heavy load might trip these flags up again. So maybe taking time to transition them into these like return to play, preseason, and all of that. Like I said, emphasize complete data collection. I think the running theme is female athletes don't have enough data, so maybe emphasize complete data collection, and then just get ready to spot these combined risks in the future. Just don't wait for like both flags to come up together to intervene. So the gap filled by our findings. So our analysis showed, like I said, none of them reached combined risk, but our previous research and other research shows that increased imbalances in muscle activities in females could make them more prone to ACL injuries, and they have different mechanical load distribution. But using our risk combined criteria, our data doesn't really show significant gender difference, but it doesn't rule it out. So it just shows that it's not reflected in our current criteria right now. So we could still see a certain female and certain males they exhibit higher symmetry or heavy load. And this just confirms that risk is not gender-based. Maybe we should bring in more individualized, more tailored, specific monitoring, not a one-size-fits-all.
A challenge we faced during this project was difficulty interpreting the data due to a lot of inconsistent measurement methods, which kind of made it difficult for us to compare data across studies and ensure that these metrics are standardized. Some metrics, for example, like the left-right max force, didn't really have units of comparison, so we had to assess it through means of limb symmetry index formula. And just to reiterate, what it does is that we had to take the stronger limb divided by weaker limb and multiply that by 100%, which gives us that symmetry index, and then taking that difference of it from 100% to derive that asymmetry index for an athlete's limb force. Another challenge we faced was the lack of data that for certain metrics compared to other metrics. For example, basketball players' data with left-right force only had 39 players around within the range of 0.1% to 22.8% asymmetry, while other metrics like acceleration load metric have far greater numbers in terms of data. Um, as for future improvements and future researches, finding specific thresholds for metric comparisons, for example, accumulated acceleration load and left-right max force asymmetry, are needed because these reference points are important when it comes to like analyzing the relationship between these metrics.
All right. Nice job, guys. Um, so we're beginning to see some more themes here again, right? Gender. So now it's groups 1, 2, and 4 have all sort of tackled or incorporated something here related to that, like your hypothesis makes sense. Another example also of this, 10 to 15% threshold seems like that's kind of like a commonality that we're seeing across a number of different metrics now. Some type of percent change within that 10 to 15, call it 10 to 20% range. Joe, you made a good point. Low risk does not mean no risk. Something important to keep on thinking about. Related to one of the final points here, I'll say and pass it over to anybody else is the units of measurement. This is something that Sean and I have also spent time, either cleaning up, doing transformations, and just kind of figuring out what to do with that data. And some of these tools, they don't really give you options out of the box to convert to standard or, whether it's in SI and then convert it to American units. But it's a problem, right? That you want to be able to get your metrics on the same unit. Um, so a future point or idea, and this is also for anybody else, something that we could do is like a Z-score transformation. So then we convert the numbers or some other type of logarithmic transformation. So all of the numbers are on the same scale between 0 to 1. And then what that does is then we're just sort of looking at magnitudes of change within that limited scale. Um, so something that we do a lot with like survey instruments, if we're trying to compare, say, one survey instrument to another survey instrument, but one is on a scale between 0 to 10 and the other is on the scale between, say, 200 to 500. But anyway, overall, really, really nice job. Sean, any sort of thoughts here?
Yeah, it was great. I just want to get everybody more clean data because these ideas the ideas are flowing, and honestly the limitations are the data right now. So excellent
Yeah,
job.
yeah, yeah. It's kind of feedback for ourselves.
Yeah. Well,
Um,
we're just interpreters of the data, but yeah, sure.
yeah, yeah. Briggs, something on your end?
Yeah, so from what I understand, I used to play state level squash in India, and I have gone a little bit. I don't know if everybody knows what squash is. It's a racket game, just like uh, you know indoor tennis, if you may, or like racquetball. So, anytime if you go to a lab, if you go to a lab, if you go to Northwell or if you go to uh, Quest or something else, they'll have different metrics. So every university, from my understanding, here also and from our research, every university interprets these baselines on their own. So we don't know what you guys are also just doing the data. So the logic behind it, whoever has derived that logic, they work with physiatrists and other people to derive those logics. So if you have a handle of that logic, I think it can really help in firstly basing it and comparing it, because that comparator is important in any data analytics. So that was the first point I had. The other point that I really wish I could expand during our presentation was the mental health aspect. No metric measures mental health, and many times mental health is a big, big, big aspect that impacts, uh, you know, sports performance. In case women, they have their own women health issues. So yeah, there are these open-ended questions.
Mhm. Yeah, no, that's a good point. And we're only looking at certain types of data. Again, I think that some of that information does exist, just not included here, but it would be interesting to combine together at some point in the future to answer and be able to ask more health-related questions. All right, so we got two more groups left between 5 and 6. Let's just go with number 6 now. Group number 6. All right, we can see your screen, so feel free to start whenever.
Right. So for our group, our research question and purpose is how does force play and GPS metrics change over time, and can they identify fatigue or abnormal workload? And then for our purpose is to analyze these metrics that we chose over time to support these athletes' readiness and training decisions. Okay. So why this matters? Because performance monitoring is essential in athletics because these athletes experience constant changes in mechanical loads, such as their neuromuscular readiness and day-to-day fatigue. To monitor these changes effectively, we rely on a key set of metrics. Some is the jump height, which represents lower body explosive power, and it decreases when the neuromuscular system is fatigued. Also have the CMJ jump height and RSI. It's consistently linked with neuromuscular fatigue also. and slower force production and reduce the readiness. The accumulated acceleration load, or the AAL, represents the acceleration, deceleration, stops, impacts, and direction changes, which are measured by the GPS or LPS. AAL spikes create high neuromechanical fatigue, which the athlete may not recover in within a short time. And then peak propulsive force also matters because it reflects how much maximal force an athlete can generate during explosive moments, such as jumping, sprinting, and acceleration. By analyzing longitudinal trends and ensuring that all the data are collected by force plate, GPS, and positional metrics are consistent, allowing better management of athlete performance and fatigue. So then we can better understand how these athletes respond to training over time, performance changes, and provide insight that supports athletes' health through consistent monitoring. Next. So these are the selected metrics that I just explained earlier, that from the Hawkins force plate is jump height, RSI, peak propulsive force, and then from the Connexion's GPS is the AAL and then total distance. Our goal is to understand whether these consistent trends in these metrics can be used to support these athletes' monitoring and inform training decisions and detect early signs of fatigue or performance decline. And I'll hand it over to Aima.
Okay, so now I'm going to go more into our data quality by showing our dashboard. So first we evaluate data quality by identifying missing records for our selected metrics. So we see here that accumulated acceleration load and total distance had some missing values, but they represented only a small percentage of the data. And then over here, we calculate team coverage. So it's the percentage of athletes with at least 5 of the measurements. And then we can see how many of the athletes were tested and then the percentage. So over here, we have the team relative performance. So we calculated each athlete's mean relative to their team, along with their percent difference and Z-score. And across most of the metrics, we saw that men's and women's basketball consistently show the top performers. So we decided to choose this to focus on our analysis. And then down here we have we selected 2 athletes from the men's basketball team with the most recorded measurements and analyzed their performance trends over just this past year. And we can see that like one of them was increasing a little bit, and then the other one has like a linear regression that's kind of decreasing. But from here we can see like some of their peak performances. So for the key findings, I'm going to quickly go over the results we got from parts 3.2 and 3.3. So this was our statistical comparison between men's basketball and women's basketball. And for this, we ran 2 t-tests for each of the metrics and then created plots to compare the performance. So I'm going to start with the Connexon metrics. For this, both teams had very similar movement demands. The accumulated acceleration load had around 9,000 samples from the men and 8,000 from the women, and the women's team showed slightly higher acceleration load, and that difference was statistically significant with a p-value of around 0.004, but not enough to have an impact. And then for total distance, with the same amount of samples, the difference was not significant with the p-value of 0.1. And that makes sense because both teams practice on the same size court and move similarly, so the overall distance covered ends up being pretty similar. And then these are just a quick visual of the box plots we created in Colab for this. And then for the Hawkins metrics, the differences were much larger. The men's basketball scored significantly higher in jump height, peak propulsive force, and RSI. And taking a look at the numbers, the t values are really large with very small p values. And these are really strong differences, and they do align with the idea that Rajul's going to get more into this later on, but that male basketball athletes typically produce higher power and force and reactivity in sports. And these are the plots for those.
And so looking at testing frequency over time, both teams show clear seasonal patterns. So we saw higher testing during the competitive season and lower testing during the summer and winter breaks, which is expected. And then women's basketball shows slightly higher peaks in some months, which may reflect more consistent data collection during that time. And then across all the sports, the testing peaks during preseason and in-season periods, especially between 2022 and 2024. That's when it peaks, and then it drops off during the breaks. And Connexon becomes the most dominant data source across the department. It has much higher monthly totals, and even with the seasonal dips, it's still consistently high, showing how much of a overall how much of the overall monitoring it's behind.
I'll continue by comparing our Hawkins jump performance results with what the literature reports for collegiate athletes. In our data set, the men's team consistently showed higher jump height, peak propulsive force, and RSI compared to the women's team. And those differences were statistically very strong. The actual values were found roughly zero point 0.4 to 0.45 meters for men and 0.25 to 0.32 meters for women, which fall within the normal ranges published for NCAA and elite athletes. The research explains this pattern through things like greater lean mass, tendon stiffness, and power output in male athletes. So overall, our jump metrics align very closely with what the literature already shows. For Connexon workload metrics, our total distance findings matched the literature almost exactly. There wasn't a meaningful difference between the men's and the women's teams, which makes sense since both teams typically cover similar movement and volumes in basketball. The more notable result was the accumulated acceleration load. The women's team had slightly higher values, and even though the effect was small, it was statistically significant. This supports what research says about acceleration-based metrics. They capture rapid stops, changes of direction, and explosive actions that total distance can't. So this metric helps reveal subtle differences in how each team might be moving throughout training or games. Looking at testing frequency over time, our patterns lined up well with the NCAA training cycle, more testing during preseason and in-season, and clear drops during the academic breaks and off-season periods. We also saw the combined use of Hawkins, Connexon, and VALD, which reflects the broader shift towards integrated athlete monitoring in collegiate sports. What our analysis adds to the existing literature is the direct comparison between men's and women's basketball while linking jump performance with workload metrics in the same data set. That combination, especially with women's data, is still relatively limited in research, so our findings help contribute to that growing area.
And here's how our flagging system works in practice. So we use three thresholds: jump height, RSI, and AAL, as well as total distance. So for jump height or RSI, when they drop 10% below an athlete's baseline, these jump metrics are usually highly reliable, and a decline of that size indicates a real neuromuscular fatigue. AAL, when a session goes above 150% of an athlete's weekly average, these spikes can reflect high mechanical stress linked to elevated risk. Third, total distance when it falls below 80% of the position norms, which can usually signal under recovery or reduced participation. These thresholds can help coaches detect fatigue, overload, and abnormal workload early and using simple and individualized rules. Next slide, please. So like I was saying, the recommendations for the coach or trainers, they could use the drop in jump height or RSI as a cue to reduce intensity or add recovery. AAL spikes can be treated as red flag sessions due to the high mechanical stress, and distance below 80% of the norm should trigger a check for fatigue, limited engagement, or early injury risk. In terms of addressing the gaps, most research look at these metrics separately, but athlete readiness is multidimensional. Our system combines neuromuscular, mechanical, and volume-based data into a single practical work form that allows staff to make earlier and more accurate decisions in terms of their team.
All right, so just to highlight a few of our data limitations we encountered. Firstly, we had the team names in the database were inconsistent, so we had to clean and standardize them to make sure that all of the metrics were aligned properly. And then some of the metrics were also unevenly available across teams because different sports were relying on different equipment. So for example, Kinexon was used far more consistently than Hawkins or Evolved, which meant the GPS-based workload metrics had stronger coverage than the jump metrics. And just going towards our future work, we're focusing on strengthening the consistency and predictive value of the monitoring system. And one priority is improving our alignment across teams and equipment sources so that each metric is collected even more evenly. Increasing the testing frequency will also help us capture cleaner performance trends and reduce the gaps caused by long breaks. Finally, with like a larger and more consistent data set, we can move towards predictive modeling, which would allow us to forecast the fatigue patterns and identify early signs of overload and support coaches and be more proactive with our data-driven decision making. Um, just moving on to the next slide. We did have a question because we knew that Sean and then obviously our professor was going to be here and we wanted to ask for your input. We are still trying to polish off our paper and everything, so we'd love your input on like as we continue refining our flagging system, do you recommend any specific statistical or coding approaches to validate whether our thresholds are too sensitive or not sensitive enough? Thank you.
All right, nice job, guys. So just a couple quick thoughts here, and I'm sure Sean will share some of these as well. The Tableau dashboard, really like that you also have something visualized there for the quality of the data. That was quite nice to see. Related to also why I think we see more Connexion data than Hawkins or Vald. This is something that we also see within healthcare. Like my hypothesis is the Connexion devices you just install and forget it, player slaps it on, versus when we look at the Vald and Hawkins devices, those actually require the player to go out of their way and do something on those devices. So it's kind of the difference between a passive data collection strategy and an active data collection strategy, if we were to use those phrases. And then for this question, I think it's a really good one. What I'd say is what you typically try and do first is you want to see what is the most similar existing flagging system out there that's validated and out in the literature, and then try and then replicate that system with your own data, in addition to then comparing it to whatever the new novel flagging approach is that you all have come up with, right? So if there's a flagging approach that's already out there in the literature that describes how it's operationalized, like what the calculations are, you then replicate that with your own data. And then you could sort of do that A/B comparison of is it underperforming or overperforming based on what the standard is. And I'll pass it over to Sean, see if you want to add on anything to that.
Yeah, that's kind of where I was going to go, especially in the time frame that you all have to work on this, right? So with the compressed schedule and scope, right? You're gonna want to lean on what's there to start. And I think even one that I saw that you had, like the AAL flag, was pretty close to what they were actually using. I think they were using something with standard deviation over the week or something like that. I forget exactly for football. But yeah, especially with the scope. Longer term, maybe you get involved with being around the team, and like if you're working for the team, there's more getting that contextual stuff to see how it works and test it and try something else and test it again. But I think the approach right now is, yeah, focus on that literature, focus on what's out there and see how it works for you.
Mhm.
All right, thank you.
Also, nice visualizations, guys. They were great.
Yeah, great job there. All right, last but not least, let's move on to the final group number 5. Okay, we can
Can
see
I move
your
to the next slide?
screen, so feel free to get started.
All right, let's go.
Okay, our group will be presenting our analysis for the project where we examine athlete monitoring data across force plate, GPS, and strength systems. So our goal was to integrate these different data streams to better understand athlete readiness, workload response, and potential areas of performance concern. So this allowed us to look at real-world collegiate sport data and evaluate how well current monitoring practices captured changes in athlete performance over time. Next slide, please. Our research question is, how do neuromuscular performances, metrics, GPS-deprived workload, and strength asymmetry interact over time, and can changes in these metrics signal readiness, fatigue, or undertraining? So this question reflects the broader goal of understanding whether we can use objective data to detect meaningful performance trends in real time. So we did develop 2 hypotheses to guide our analysis. So hypothesis 1 states that athletes who experience periods of high external load or particularly elevated acceleration load will demonstrate short-term reductions in jump height and peak propulsive power relative to their baseline. So this is based on prior research linking acceleration-based workload to neuromuscular fatigue. And hypothesis 2 proposes that athletes with greater max force asymmetry will show more variability in their counter movement jump and performance, and may respond differently to training loads compared to athletes who are more symmetrical. This aligns with literature suggesting that asymmetry can influence mechanical efficiency and fatigue patterns. So these hypotheses give us a framework to assess whether our metrics behaved in predictable, meaningful ways over time.
So, although many teams collect force plates, GPS, and strength data, the literature shows several gaps. For example, while CMJ data is useful for fatigue monitoring, it is often analyzed alone. GPS workload, particularly accelerations, is strongly associated with neuromuscular stress, but it is rarely paired with force plate data. Strength asymmetry is typically also studied in isolation without connection to longitudinal workload or CMJ decline. So the clear gap here is that the teams rarely integrate all these 3 systems into a unified readiness or monitoring framework. Next slide, please. So our analysis focuses on 5 metrics selected for their strong representation in the database and robust support in the sports science and literature. So first we chose the jump height and peak propulsive power from Hawkins force plates, since they are widely used to assess lower body explosive power and neuromuscular readiness. And both of these have also been linked to sprint acceleration, change of direction ability, and fatigue-related declines. And then we also chose total distance and accumulated acceleration load from Kinexon GPS units. And these capture volume and intensity related external workloads. Total distance provides a global measure of session volume, while acceleration loads reflects the mechanical stress of repeated acceleration and decelerations. And lastly, we chose the max force left and right values from valve systems, since it provides unilateral strength information and enables qualification of inner limb asymmetry, which is a factor frequently examined in injury prevention literature. Next.
So in order to clean the data, we first pull the data from the MySQL table, research experiment with factor test. Then we make sure to remove all the rows with the missing player, team, metric, and value just to clean it up a bit. Then we standardized the timestamps. We retained the original team labels for authenticity. We added a long format structure. We reflected real-world testing inconsistencies. And then for the analytical approach, we make sure that it's a literature-based flagging threshold with inactivity of greater than 30 days without testing, a performance decline of more than 10% below the 3-test rolling mean, 2 standard deviation from the team mean for a team deviation, a greater than 10% left-right difference for asymmetry, and then we exported these flag results to the part 4 flagged athlete.csv file.
So now let's get on to the actual data. Can everyone hear me? I wasn't sure. But yeah, so the way how we're presenting this data, we're using a heat map. So overall, this information shows for each unique player. We made sure that there weren't any duplicates, as we all spoken before about the standardization of the data. But the most important information here that as you can see is highlighted in dark green is the outside standard deviation of 2, which is the accelerated load accumulation of 2,982 athletes. Again, this is on an overall scale. We just wanted to have a overall summary of all the players within the system to then move forward into team play. And then we move forward to the inactivity. The inactivity of we as a group, we automatically assume that it's just because of no longer being in the team, but overall from these studies, this could come from fatigue. As we learned before, Sean was saying that sometimes they just would wear the machines on them to actually record the information that they're doing for that session, that team session, and we can see for the decline of 10%, there's on quite a few aspects. Again, in regards to what we plan to move forward with regarding teams, we will have one for standardization for each teams, and of course, the final thing is the asymmetry, as we know that having leaning over to the left or the right side can cause for injury, and we saw that this happened for 217 players.
So while we were cleaning the data, we found some limitations. One of the limitations was the inconsistent testing frequency. So some athletes were measured weekly while others were only measured a couple of times. There was also missing or sparse data, and if a data set has a null or zero value, it limits its statistical strength. Another limitation we noticed was the lack of contextual variables. We never knew why the metrics changed. Was it from an injury? Was it from a training load? Was it maybe the team just doesn't work well together? So for our future research, what we want to do is we want to standardize and increase the testing frequency. We want to make sure that similar data collection times are collected, and this would help increase accuracy. We want to integrate contextual data to explain why the metrics changed. We would also like to expand beyond one institution just as a comparison against other institutions, because that would reveal universal versus contextual specific patterns. But our immediate next steps would be to compare the data year by year. We would select the same sports and look at them year by year to see why the metrics for those sports during that year improved or if it got worse and why. So we would see between let's say the soccer team for 2023 and 2024, we would see why the metrics changed. Was it because the new players were added that didn't mesh well with the team? Was it that maybe there was a different training regime? Or was it that maybe there was a different coaching style? And then our question is, so when applying these flagging functions, is it more effective to evaluate at the individual athlete level, at the team level, or at a combined model that accounts for both of them?
And the final thing that we have here just to show is regarding the testing frequency. We are planning to implement this hopefully regarding the aspect of the flagging with the frequencies, but we decided to just use men's and women's basketball as an example, as quite a few of our classmates talked about of finding actually the right group to do it. SQL didn't like the comma, so we had to do a whole lot of fixtures regarding that. But there's quite a few inconsistencies of the frequency of, as we've seen with multiple other classmates, regarding men's sports and women's sports as well. So we can definitely see here in the span of 2022, from my knowledge, the women's basketball team was doing really good at that time. So I'm assuming that includes why there was so much testing frequency. There's a drastic difference between men's basketball and women's basketball. But as we go along with the graph, there's quite a bit of difference. And I think the biggest one that we thought of like why is there such a big difference? Because this not frequency is not by the amount doing it. It's just like how frequent as they're doing. Of course, as it was within 2024 to 2025, within the middle to the end of the year, there's quite a big inconsistencies as well. And then we move on to 2025. With the information to go into the frequencies as well. And we just have one more to show after here. Finally, into the testing for the Connexion and the Vlad and the Hawkins, which we also wanted to look into as Angel talked about before in regards to testing. I know other group talked about this, so we did it by not only by quarterly for each year. As you can see, massive difference, but we also did for 2025 in itself for each specific month of which months were not seen as much testings for the different data sources. And that is our presentation.
Awesome. Great job, guys. So just a couple quick thoughts here. Then I'll pass it over to Sean. Um, yeah, good job articulating the hypotheses. I think you're one of the few groups that did all three of the devices in terms of incorporating them. Um, Also like the idea of the interlimb symmetry, so getting to a very specific type of asymmetry measure. Heat maps were good, like those. We hadn't seen those yet. Also good point around the contextualization of comparing Stony Brook to maybe other different Division One teams. And I think that's one of the big challenges is different groups use different devices and calculate things differently, but not to say that it can't be done, and it probably should be done. And lastly, related to your question, I think why not do it all, right? And sort of compare. I think it'd be interesting to see how these things change at either, and I forget if you definitely said individual and team level, but then there's also position level. I don't know if that was one of the other layers that you sort of added in there, but like let's say for basketball or football, right? You have a bunch of different players that play the same position. So then you could also kind of, perform like a gamification at the position level, right? To sort of see who's the highest performing or lowest performing at, whether they're outfielder in baseball or maybe a wide receiver in football land. Um, yeah, I'll pass it over to Sean.
Yeah, Briggs, did you want to chime in with a question?
No, I'll follow you if you want to do this.
Oh, sure. Okay. Yeah, I kind of was echoing Hans's in my head was all three. Yeah, taking on all three is a big challenge. Good job with that. Well executed. And I answered this question here. I think looking at it as a flow in terms of the athlete flags lead into the position flags lead into the team flags, right? Or it's just athlete into team, right? I think they will be most interested um, in who at that level is receiving those flags, particularly because it's just so individual and things are so different. I think it will roll up to saying whether or not the overall health of the team is high or low, but because everyone is so different, I think starting at that individual level is super important. Yeah, kick it over to Briggs.
Yeah, so that was a very relevant question, Arav. We though it's out of the scope of this project, but we thought of a composite index. We have a derived metric which is only taking means. But if we look at the real world data, the derived metrics are derived from various other metrics. So once we have a derived metric and a composite index, of which we have a derived metric, that is obviously going to be very meaningful because taking them individually is probably not that helpful. But if you have a derived metric and there is a logic behind it, nothing is 100%. But yeah, so that was something that we thought of, but then yeah, we didn't want to put the effort. But yeah, a derived metric based on a composite index, yeah, that's I think generally how the real world would probably work.
Mm-hmm. Yeah. Yeah, completely agree. See a lot of the combined matrices or metrics. Um, to kind of come up with your own unique proprietary score, right?
I think football's using a five combination system. If someone trips five indicators, they hold them out of practice.
Huh. No, really.
I think so, somewhere
Hmm.
around that.
Yeah. Well, so before I say my final thoughts and comments, maybe let you, I know you had a couple ideas to sort of share, just like couple general thoughts, Sean, and then
Yeah.
we could let you jump off since it's getting a little bit late here.
Yeah, all good. No, thank you everybody. I really appreciate the effort you put into these. It shows. These are not easy projects to put together, especially with the data cleaning and the, thinking about where you're going to go with it all. It's overwhelming to start, and the way you all were able to synthesize down into something meaningful was excellent. And just from a general perspective, the communication skills in the room are high. You all clear, concise, and easy to follow along with. Those skills will benefit you all in the future wherever you may go. You know, take some pride in what you put together. These projects were really, really good. I had a great time joining you. I appreciate that. Hans, let me know what I can do in the future. And like I said, if anybody has, questions about just what I do or what skills you might want to work on or anything like that, I'm happy to chime in where I can. My just one opinion, but happy to add it to you all.
Awesome. Yeah, and I'll echo what Sean said in just a minute. But yeah, Sean, thank you again for joining. Quick
All
round of
right.
applause for Sean. And then I'll be also sharing some of our comments that we have in notes to each of the groups. So you all will also get some sort of written feedback and things to think about. But thanks again, Sean.
All right. Thanks for having me, everybody. Take care.
Thank you.
All right, so just very quick on my end in terms of a couple house cleaning things, and yeah, you guys did excellent. I think these are probably some of the highest caliber presentations I've seen in a while. One thing that I would recommend that each of your groups do, there's going to be a research day in the School of Health Professions in end of April. It's a symposium where there's also poster presentations, and each of your groups, I think, would qualify for doing a poster if you want to. It's also a peer-reviewed process, so this would technically be a sort of peer-reviewed work if your abstract gets accepted to our research day. It would be something that you'd be able to flag as a as peer-reviewed scholarly work. So I'll be sure to forward that email once it comes out, and just in case you miss it. Usually it'll come out probably sometime between now and January to February. So that just is me emphasizing that I think you all did a phenomenal job on this, and I'm really looking forward to seeing what the final products are. And I think a lot of what you all put together is very publishable and unique and really, really interesting. So with that, what we'll do next is we'll just have like a brief class on Monday night just to kind of do some like final housekeeping stuff. And then we're all done with our theoretical lectures and stuff like that. And again, we're not even going to really talk too much about anything substantive on Monday night. But if everyone can still please join the Zoom for next Monday. And then that will be kind of our sort of final close off session and wrapping up any sort of final in-person quote questions that you all might have. So yeah, round of applause to you all. Really, really interesting work. And hopefully you all found it interesting to also see what your peers did. So, all right, everybody. Well, have a good rest of the evening. Good job again, and I'll see you all next week.
Good night.
Thank
Thank
you.
you.
Have a good
Good
night.
night. Thank you,
Thank
Professor.
you.
Good night,
All
Professor.
right, bye,
Thank
everybody.
you.
Professor, I actually have a quick question. So
Yeah,
we're
sure.
still able to make adjustments to our project, right? So
Yeah.
the final, like I guess a set date would be like next week, or would it be like the 18th?
Yeah, it'd be like the week after next. It'd probably be like a day or two before the semester ends, and that's what we'll talk about next week. Because I want to give you guys some time to then also I gotta summarize my feedback and Sean's. So we were taking notes and sharing notes during the presentation. So I'm going to compile that together and then share it with you also. You could at least sort of see what we found to be interesting in the questions that we were asking ourselves as you
Yeah.
were going through the material.
Quick
Okay.
question.
Yeah.
Hans. So can you give us written feedback because that'll help, all this is good, but then if you can give us a brief, like 3, 4, 5 pointers on the
Yeah.
presentation,
Yeah.
and
Yeah.
then
And I'm looking at my notes and Sean's notes right now. We
yeah,
have
yeah,
at
yeah.
least like, you know, 10 to 15 bullet points for each presentation that we'll be able to provide to you
Yeah,
all.
because the other thing is, not everybody is same level in terms of presenting and all that. So that this is again, I keep keep talking in the teams. When we work in teams, let's look at it as working in a team, so that if you don't work together, a patient is going to get impacted. So
Mhm.
if they get good feedback, this is also training for get better work ethic and all. But
Yeah.
yeah, great. I think it was a great way that you did that. But we did miss the MRSI, so